Hello there and welcome to Life Beyond Seen, where curiosity slows its breathing, science lowers its voice, and the world feels just a little wider than it did a moment ago. Wherever you are right now, whether you're easing into sleep, resting your eyes after a long day, or simply letting your thoughts drift, I'm glad you're here. Tonight, we're heading somewhere very far away without moving at all, somewhere deep, quiet, and still largely untouched, somewhere that humans have visited only a handful of times, despite having mapped planets, walked on the moon, and sent machines beyond the edge of the solar system. Tonight, we're going down. Not quickly, not dramatically, just slowly enough to notice what changes along the way. The ocean covers more than 70% of our planet, yet most of it remains unseen, unexplored, and quietly indifferent to our presence. We skim across its surface in ships. We dip beneath it in submarines. We study it with satellites and sensors. But beneath all of that familiar blue lies a depth that feels less like a place and more like a boundary, a reminder, a firm line drawn by nature that says, very politely and very firmly, you may visit, but you may not stay. At the centre of that boundary is the Mariana Trench. It's the deepest known point in Earth's oceans, a long, narrow scar in the planet's crust that plunges downward for nearly 11 kilometres, a place so deep that if you dropped Mount Everest into it, the peak would still be underwater. A place where pressure doesn't just increase, it dominates, where darkness is complete, where sound behaves strangely, where time, perception, and even material strength begin to behave differently than they do up here. And despite decades of technological progress, despite all our clever materials, robotics and calculations, this trench still resists us. We've touched it. We've measured it. We've sent a few brave humans down and brought them back. But going deeper, staying longer, building anything permanent, or treating it like a place we can truly inhabit, that remains out of reach. So the question that will quietly guide us tonight is a simple one. Why? Why, in a world where humans can orbit the Earth every 90 minutes, does this narrow trench beneath the Pacific Ocean still refuse to let us go deeper? What exactly stops us? And why does the ocean, of all places, remain more forbidding than outer space? Before we begin that descent together, let me pause for just a moment and ask something gentle and grounding. Where are you listening from right now? Is it late where you are, with lights dimmed and the day already loosening its grip? Or is the world still moving outside your window while you settle into this quieter space? And if you happen to glance at the time, notice how steady it looks up here, how reliable, how unremarkable. Down below, time feels different. Not because it changes, but because everything around it does. If you find this kind of slow exploration calming, interesting, or simply a good companion for rest, a like or a subscription helps this little space reach others who might enjoy wandering through these questions too. No rush, no pressure, just a quiet nod if it feels right. Now let's begin. Imagine standing at the edge of the Pacific Ocean. The surface is familiar, waves roll in patterns you've seen all your life. Light reflects, scatters, dances. Ships move confidently across it, their hulls slicing through water that seems almost welcoming. Beneath that surface, fish move through sunlit layers, coral reefs cluster with life, and currents carry warmth and nutrients across entire hemispheres. But as you descend, even in imagination, things begin to change almost immediately. Light fades first. Reds disappear within the first few meters. Oranges follow. Yellows soften and vanish. Blues linger the longest, then finally surrender too. Within a few hundred meters, the ocean is no longer illuminated by the sun. It's lit only by what lives there. Flickers, glows, brief signals in the dark. Pressure begins to assert itself long before the darkness feels complete. Every 10 meters adds another atmosphere of pressure, another layer of weight pressing in from all sides. At the surface, your body is perfectly balanced against one atmosphere of air. At 100 meters, the pressure has increased tenfold. At 1,000 meters, it's crushing by comparison. And the Mariana Trench goes far beyond that. By the time you reach its deepest point, the pressure is more than 1,000 times what you feel right now. That's not poetic exaggeration. That's math. It's the equivalent of having dozens of fully loaded jetliners stacked on every square meter of your body. And the ocean applies that force evenly, relentlessly, without pause. Nothing human was designed for this. Our bodies evolved for land, for air, for gravity acting downward, not inward from every direction at once. Even our strongest materials, the ones we trust to build skyscrapers and spacecraft, behave differently under that kind of load. Metals compress, glass thickens and distorts, tiny flaws become fatal weaknesses, and yet we try. Over the past century, humans have built vessels specifically designed to challenge this depth. Thick-walled submersibles shaped like spheres, because spheres distribute pressure evenly. Windows made from acrylic blocks tens of centimeters thick. Electronics sealed inside pressure-resistant housings. Systems designed not for comfort, but for survival. Each descent is slow, painfully slow. Hours of controlled sinking. Every sound is amplified. Every creak becomes noticeable. Every vibration feels personal. There's no quick escape route, no nearby rescue. Just water above, below, and all around. And that's for missions that last only a few hours. The Mariana Trench doesn't just test technology, it tests patience, planning, psychology. It exposes how fragile our margin for error really is. Up here, on land, mistakes are often recoverable. Down there, mistakes are final. That alone explains part of the resistance, but not all of it. Because humans don't stop at practical limits easily. We push against deserts, mountains, polar ice and vacuum. We adapt, we innovate, we insist. So why has the deep ocean, and especially this trench, remained such a stubborn exception? Part of the answer lies in how hostile the environment truly is, not in dramatic ways, but in subtle ones. Pressure is obvious, but it's not alone. Temperature near the trench hovers just above freezing. Corrosive salt water infiltrates microscopic gaps. Communication becomes unreliable. Radio waves don't travel through water the way they do through air. Even light-based communication fails at depth. To speak with a vessel in the trench, we rely on sound. Slow, delayed, distorted sound. Messages take time to arrive. Control is never immediate. If something goes wrong, help cannot respond quickly enough to matter. And then there's the ocean itself. Not calm, not still, not empty. Currents move even at depth. Sediment shifts. The seafloor isn't a flat plain, but a landscape of slopes, ridges, and collapses. The trench is geologically active. It exists because massive tectonic plates collide and slide beneath one another. Earthquakes are not hypothetical here. They're expected. Building something permanent in that environment would be like trying to build a house on a moving staircase while holding your breath indefinitely. But perhaps the most unsettling part is this. The Mariana Trench does not need to be dangerous. It already is. Without intention, without malice, without effort. It simply exists in conditions that do not tolerate human presence. And yet, life thrives there. Creatures adapted to pressure that would crush us instantly. Organisms that don't rely on sunlight, that metabolize chemicals seeping from the earth itself. Fish with flexible bones. Microbes that treat toxic compounds as fuel. Entire ecosystems operating quietly, efficiently, without ever noticing that we exist above them. This contrast matters, because it shows that the problem is not depth alone, it's compatibility. The trench doesn't block humans because it's empty or lifeless. It blocks us because it is alive in a way we are not built to join. As we move forward from here, we'll take our time exploring each of the barriers that stand between humans and greater depths. Not just the physical ones, but but the technological, logistical and psychological limits that stack up layer by layer. We'll look at what happens when machines fail, why rescue missions are nearly impossible, why pressure doesn't forgive even tiny errors, and why, despite all our ambition, the ocean still sets the terms. For now, let yourself stay near the surface just a little longer. Let the idea of depth settle in, not as something dramatic or frightening, but as something steady, constant, and patient. The Mariana Trench has been waiting for millions of years. It isn't going anywhere, and it has plenty of time to remind us that going deeper is not the same as going farther. The deepest place we know exists is not hidden by distance, but by depth. It sits on our own planet, beneath water we cross daily without a second thought, beneath shipping lanes, weather systems, and satellites that pass overhead unaware of what lies below. While Mars feels distant and space feels unreachable, this place has been here the entire time, pressing quietly into the Earth's crust, deeper than any canyon on land, deeper than any mine, deeper than human intuition comfortably allows. The Mariana Trench is not a single hole or a neat vertical drop. It is a long, curved depression in the western Pacific Ocean, stretching for more than 2,500 kilometers. Its shape follows the slow, relentless movement of tectonic plates, where the Pacific Plate is forced beneath the smaller Mariana Plate. This process, called subduction, happens at a pace so slow it escapes notice in a single lifetime. Yet over millions of years it has carved the deepest wound on the planet's surface. At its deepest point lies a region known as the Challenger Deep. This is the number that tends to appear in books, documentaries, and trivia questions. Roughly 10,900 meters below sea level, nearly 11 kilometers, a depth so extreme that numbers alone struggle to communicate what it means. If the tallest mountain on Earth were placed inside it, there would still be water above the peak. If every building in a major city were stacked end to end, they would not reach the surface. But the significance of the trench is not just that it is deep, it is that it represents a limit, a natural endpoint to how far the planet allows us to go before conditions become fundamentally incompatible with the way humans exist. The deeper one goes into the ocean, the less the environment resembles anything familiar. This is not a gradual shift from comfortable to uncomfortable. It is a steady accumulation of changes that eventually cross a threshold. Beyond that point, intuition fails, physics takes over, the body becomes irrelevant. At the surface, water feels light, almost playful. It supports swimmers, carries boats, reflects sunlight. It moves when pushed. At depth, water becomes something else entirely. It becomes weight. It becomes force. It becomes an all-encompassing presence that presses inward equally from every direction, leaving no weak side, no relief, no escape from its influence. At Challenger Deep, the pressure reaches more than 100 megapascals. That number sounds technical, but its meaning is simple. Every square centimetre of a human body would experience a force equivalent to more than 1,000 kilograms, not pulling down, but squeezing in. Bones, organs, and tissues are not built for this. Even steel structures must be carefully shaped and reinforced to avoid catastrophic collapse. What makes this more difficult to comprehend is that pressure is invisible. There is no sensation of being pressed until something fails. A vessel does not gradually crumple like a soda can. It holds, and then it doesn't. The transition between safe and destroyed is measured in fractions of a second. This is part of what gives the Mariana Trench its reputation as a place that does not forgive mistakes. On land, errors can often be corrected. In aviation, redundancy exists. In space, risks are high, but systems are designed with multiple layers of backup and constant monitoring. In the deepest ocean, redundancy helps, but distance removes the possibility of intervention. The deepest place we know exists is not simply hard to reach, it is hard to return from. Only a handful of human beings have ever been there. Fewer people have visited Challenger Deep than have walked on the moon. Each descent required years of planning, specialized vehicles, and acceptance of the fact that if something went wrong, there would be no rescue. Not in minutes, not in hours, not at all. The first successful human descent occurred in 1960. A steel sphere barely large enough for two people was lowered into the trench. The vessel had no ability to move freely. It descended and ascended along a single line, dependent on ballast systems that could fail if jammed or damaged. The occupants spent a short time at the bottom, observed sediment stirred by their arrival, and then began the long ascent back to pressure levels compatible with life. Even then, the mission was not without incident. A window cracked during descent, not enough to fail, but enough to remind everyone involved how narrow the margin truly was. Decades passed before another human attempt was made. Technology improved, materials advanced, sensors became smaller and more reliable, yet the trench remained resistant. Unmanned probes could go deeper and more often, but they too faced limits. Electronics failed, housings cracked, data was lost. The environment punished every weakness. What makes the deepest place we know exists as such a persistent challenge is that it combines multiple hostile factors into one location. Pressure alone would be enough. Darkness alone would be manageable. Cold alone could be mitigated. Distance alone could be overcome. But together they form a system that resists long-term human presence. Sunlight does not reach the trench, not even faint traces. Darkness. There is not the absence of light, but a permanent condition. There is no day or night. No visual reference to the surface. Any sense of orientation must be manufactured through instruments and trust in engineering. Temperature hovers just above freezing. Not cold enough to freeze solid, but cold enough to slow chemical reactions and affect materials over time. Metals become more brittle, lubricants thicken, batteries lose efficiency. Then there is isolation. At the surface, communication is instant. Voices travel, signals bounce. At depth, communication is reduced to sound pulses that move slowly through water. Instructions sent from above arrive seconds or minutes later. Responses take just as long to return. There is no real-time conversation, only delayed confirmation. This matters because the deepest place we know exists is not just physically isolated, it is cognitively isolating. The people who descend there must operate without the reassurance of immediate contact. They must trust that the systems around them will continue functioning exactly as designed. There is no outside intervention if they don't. The trench is also geologically active. It exists because of motion. The seafloor is not stable. It shifts, compresses, and occasionally releases energy through earthquakes. These events are usually small, but their presence means the environment cannot be treated as static. Sediment can shift, slopes can collapse, visibility can drop instantly. Even the act of landing on the bottom is not simple. There is no firm ground in the way land is firm. The sediment at the bottom of the trench is fine, soft, and easily disturbed. Vehicles stir clouds of particles that can take hours to settle. Instruments must be designed to operate without clear visual cues. Navigation becomes abstract, yet despite all of this, life exists there. This is perhaps the most striking part. The deepest place we know exists is not empty. It is not barren, it is not dead. It is inhabited by organisms that evolved specifically for these conditions. Creatures with flexible structures that do not resist pressure, but accept it. Cells adapted to cold and darkness. Metabolisms that do not depend on sunlight, but on chemical gradients and slow energy flows. These organisms do not fight the environment, they are part of it. Humans, by contrast, must bring their environment with them. Air, pressure, temperature, light, communication. Everything required for survival must be manufactured, transported, and maintained. Any failure returns conditions to their natural state instantly. This is a fundamental difference between exploration of the deep ocean and exploration of space. In space, the environment is hostile but predictable. vacuum, radiation, microgravity. These factors are consistent. In the trench, conditions are stable in the long term but unforgiving in the short term. Pressure does not fluctuate, but it allows no deviation. The deepest place we know exists as a reminder that exploration is not only about distance, it is about compatibility. How far can a species move away from the conditions that shaped it before adaptation becomes impossible? For now, the answer appears to be that humans can visit the trench, but not belong to it. Each descent is a brief intrusion, a controlled interruption, a temporary presence that leaves little trace and withdraws quickly. There are no plans for permanent stations, no underwater cities, no long-term habitation at those depths. Not because of lack of imagination, but because the cost of maintaining life there grows exponentially with depth. Every additional meter adds pressure, every additional hour increases risk. Every system must function perfectly without external support. The deepest place we know exists at the intersection of curiosity and restraint. It draws attention precisely because it cannot be easily conquered. It resists the narratives of progress that assume every frontier will eventually yield. As attention shifts from the surface toward the forces that make this depth so resistant, one factor begins to dominate all others. It is not darkness, it is not cold, it is not distance, it is pressure. And once pressure enters the picture fully, everything else begins to reorganize around it. Pressure is not dramatic. It does not announce itself. It does not roar, shake, or glow. It does not rush in or surge forward. Pressure is quiet, constant, and patient, and that is exactly what makes it so unforgiving. In the deepest parts of the ocean, pressure is not something that happens to you. It is something that surrounds you completely, evenly, and without interruption. It does not care how strong something is in one direction, because it presses from every direction at once. There is no front, no back, no top, no bottom. Every surface becomes the weakest surface. At sea level, the human body lives under one atmosphere of pressure. That pressure comes from the weight of the air above us, stretching up through the sky. We do not feel it because our bodies evolved within it. Our internal pressure balances it naturally. Lungs expand and contract. Blood flows as expected. Bones hold their shape. Everything is tuned to this single, stable value. In the ocean, that balance begins to change immediately. For every 10 meters of depth, pressure increases by roughly 1 additional atmosphere. That number sounds small at first. 10 meters is the height of a tall building, something a swimmer could reach in seconds. But the increase never stops. 20 meters, 3 atmospheres. 100 meters, 11 atmospheres. 1,000 meters, over 100 atmospheres. By the time a vessel approaches the depths of the Mariana Trench, the pressure has risen to more than 1,000 atmospheres. There is nothing gradual about what that means for materials and structures. At that point, pressure is no longer a background condition. It becomes the dominant force acting on everything that exists there. What makes pressure so dangerous is that it does not need speed or motion to do damage. A collision involves energy transfer. A fire involves heat. Pressure simply exists. It waits. It presses. And if something is not designed perfectly for it, failure is immediate and absolute. Human bodies cannot survive this environment at all. No amount of training or conditioning changes that. Lungs collapse long before reaching extreme depth. Gases dissolve into tissues. Blood chemistry changes. Even if oxygen were supplied artificially, the structural integrity of the body itself would fail. Cells are not designed to be compressed uniformly beyond a certain point. Organs require shape. Pressure removes that privilege. This is why all human interaction with extreme depth depends entirely on containment. The only way to survive is to keep pressure out. Not partially, not mostly, completely. That requirement alone dictates nearly every design choice in deep-sea engineering. Pressure-resistant vessels are almost always spherical or cylindrical with rounded ends. Flat surfaces are avoided because pressure concentrates stress at edges and corners. A flat wall bows inward under pressure, creating uneven force distribution. A sphere spreads pressure evenly across its surface, minimizing weak points. Even then, materials must be extraordinarily thick. Windows, when they exist at all, are not glass in the usual sense. They are often made of acrylic or specialized composites, shaped into thick domes. Some are more than 20 centimeters thick. Even at that thickness, they flex slightly under pressure. Engineers account for that flex. They must. The hulls of deep-diving submersibles are often forged from high-strength steel or titanium alloys. Each weld is inspected repeatedly. Each seam is tested. Microscopic imperfections that would be irrelevant at the surface become fatal flaws at depth. A tiny crack can propagate instantly under uniform compression. What makes pressure particularly unforgiving is that there is no warning phase. Systems do not fail gradually. There is no time to react. Once a structure crosses its tolerance threshold, collapse happens faster than human perception can register. The implosion occurs in milliseconds. Everything inside is destroyed before nerve signals could even reach the brain. This is not theoretical. It is well understood physics. When pressure overwhelms a sealed structure, the surrounding water rushes inward at incredible speed. The energy released is immense. Temperatures spike briefly. Shock waves propagate. The event is violent, brief and final. Because of this, deep-sea vessels are designed with extreme conservatism. Engineers do not aim for materials that can barely survive expected pressure. They aim for margins, large ones. Safety factors are applied again and again. Even then, every descent is a calculated risk. Pressure also affects more than just hulls. It influences every component of a mission. Electronics behave differently under pressure. Even when sealed, internal components experience stress. Connectors compress. Insulation deforms. Materials that expand and contract normally with temperature changes are constrained. Over time, this leads to fatigue. Lubricants thicken under cold and pressure. Moving parts resist motion. Motors draw more power. Bearings wear differently. Every mechanism must be designed to function reliably in an environment where friction behaves unpredictably. Pressure also affects chemistry. Gases dissolve into liquids more readily. Materials that are stable at the surface can react differently at depth. Even plastics can become brittle or deform under long-term compression. Cables, often used to supply power or retrieve data, face their own challenges. A cable descending into extreme depth must support its own weight while resisting crushing forces. It must transmit signals reliably while remaining flexible enough not to snap. Few materials can do all of this at once. Pressure also changes how sound travels. In the deep ocean, sound moves faster and farther than it does at the surface. This is useful for communication and navigation, but it also introduces complexity. Echoes behave differently. Distances can be misjudged. Interference occurs. Because radio waves do not travel well through water, communication relies on acoustic signals. These signals are slow and limited in bandwidth. Pressure does not directly block them, but it shapes the environment in which they propagate. Communication delays are inevitable. Then there is the psychological effect of knowing that pressure is always there. For the people who have descended into the deepest parts of the ocean, the awareness is constant. Every sound becomes significant. A creak, a pop, a shift. Even though vessels are designed to flex slightly under pressure, hearing those adjustments can be unsettling. Unlike turbulence in an aircraft or vibrations in a spacecraft, pressure-related sounds do not indicate movement. They indicate load. The vessel is not being shaken, it is being held. This creates a unique mental environment. There is no sense of fighting the surroundings. There is only endurance, trust in engineering, acceptance of the fact that survival depends entirely on a thin barrier holding back an unimaginable force. Pressure also eliminates the possibility of rescue. At extreme depth, no other vessel can reach you quickly. Even if one existed nearby, matching depth and pressure safely would take hours. A compromised vessel cannot wait that long. There is no equivalent to an emergency landing, no safe harbour, no gradual ascent if structural integrity is compromised. This is why deep-sea missions are planned with extraordinary care. Redundancy exists, but it is limited by physics. Multiple systems can fail independently, but the hull cannot fail at all. There is no backup hull. Pressure also places limits on duration. Even if a vessel survives descent and remains intact, long-term exposure increases risk. Materials fatigue, seals age, systems degrade. The longer something remains at extreme depth, the more likely a small problem becomes a critical one. This is one of the reasons permanent human presence in the Mariana Trench remains unrealistic. Maintaining a pressure-resistant habitat indefinitely would require constant inspection, maintenance, and replacement of components. All of that would need to happen at depth, or require repeated ascents and descents, each carrying risk. Pressure does not allow shortcuts. It does not allow improvisation. It does not allow gradual adaptation. Either a system is designed for it, or it fails. Life that exists at these depths does not resist pressure. It avoids resisting it at all. Deep-sea organisms often lack rigid structures. Their bodies are flexible. Their cells are adapted to function while compressed. They do not maintain internal pressure differences that would cause collapse. They exist in equilibrium with their surroundings. Humans cannot do this. Our survival depends on maintaining internal environments that differ significantly from the outside world. We require air-filled spaces. We require pressure gradients. We require structure. Pressure strips away those requirements mercilessly. It is tempting to think of pressure as simply a scaled-up version of weight, as if deeper simply means heavier, but that analogy fails quickly. Weight acts downward. Pressure acts inward. Weight can be supported by structure. Pressure must be resisted everywhere at once. This distinction matters because it explains why building deeper is not like building taller. Skyscrapers deal with gravity and wind. Their load paths are well understood. Materials are stacked, reinforced, distributed. At depth, stacking does nothing. Every surface is loaded equally. As engineering improves, materials become stronger, lighter, and more reliable. But pressure increases linearly with depth. There is no technological trick that changes that relationship. Every additional meter adds force. Every design must account for that inevitability. This is why the deepest place we know continues to mark a boundary. Not because humans lack curiosity or courage, but because pressure does not negotiate. It does not compromise. It does not forgive errors, delays, or optimism. As attention moves from pressure itself to the tools we use to confront it, a pattern becomes clear. Human progress in the deep ocean has not been about conquering pressure, but about briefly tolerating it, building vessels that can endure it long enough to observe, measure, and leave. And even those vessels eventually reach limits, because pressure is not the only thing that fails under such conditions. Sometimes the machines do first. At first glance, it sounds backward. Space is a vacuum. It is cold, irradiated, and lethal to unprotected human life in seconds. The ocean, by contrast, is full of water, life, movement, and familiarity. Humans swim in it, sail on it, live beside it. So the idea that the ocean, especially the deep ocean, could be more hostile than space feels almost unfair. And yet, from an engineering, survival, and rescue standpoint, it is. The reason the ocean is more hostile than space has very little to do with drama and a great deal to do with control. In space, almost everything about the environment is extreme, but it is also simple. In the deep ocean, the environment is not only extreme, it is intrusive. It pushes back constantly. It interferes. It presses inward and refuses to be isolated from. In space, the primary challenge is absence. No air, no pressure, no protection from radiation. These are serious problems, but they are problems humans know how to define clearly. A spacecraft creates a sealed bubble of Earth-like conditions. Inside that bubble, pressure, temperature, and air composition are carefully regulated. As long as the seal holds, the environment inside behaves predictably. In the deep ocean, the challenge is presence. Too much pressure, too much water, too much force acting on every surface. The environment does not merely surround you, it insists on participation. It wants inside. This difference changes everything. A spacecraft hull must withstand internal pressure pushing outward. That pressure is relatively low, usually close to 1 atmosphere. The structure is under tension, not compression. Materials are very good at handling tension. Even thin walls can hold significant internal pressure if designed correctly. This is why aircraft cabins and space station modules do not need to be extraordinarily thick. A deep-sea vessel faces the opposite problem. Pressure pushes inward. Compression is far harder to manage. Materials buckle. Tiny imperfections become collapse points. Thickness increases weight, which introduces new challenges. Shapes become limited. Design flexibility disappears. In space, if a spacecraft loses pressure, the danger is immediate, but the forces involved are comparatively small. Air rushes out, systems fail. The situation is catastrophic, but the physical destruction is limited. In the deep ocean, if a vessel loses integrity, the surrounding water rushes in with overwhelming force. The event is not just fatal, it is annihilating. Then there is gravity. In space, microgravity simplifies many problems. Objects float. Structures are not bearing their own weight. Components do not sag or compress under load. This allows large structures to be assembled from relatively delicate parts. The International Space Station is vast, but its components would collapse under their own weight if placed on Earth. In the deep ocean, gravity still matters. A vessel must support its own mass while also resisting external pressure. Every component must function while being compressed and pulled downward. There is no relief from load in any direction. Communication is another major difference. In space, radio communication is straightforward. Signals travel at the speed of light. Bandwidth is high. Real-time voice and video are possible even over vast distances, with only small delays. A spacecraft in low Earth orbit can maintain constant contact with mission control. Astronauts are never truly isolated. In the deep ocean, radio waves are almost useless. Water absorbs them quickly. Communication relies on sound, which travels far but slowly and imprecisely. Data rates are low. Messages are delayed. Complex instructions are difficult to transmit. There is no continuous conversation. This isolation has practical consequences. In space, if a system behaves unexpectedly, engineers on the ground can analyze data and provide guidance immediately. In the deep ocean, operators must act independently, often without knowing whether help even received their last message. Rescue capabilities reveal the contrast even more sharply. If a spacecraft experiences trouble in low Earth orbit, rescue options exist. Other spacecraft can be launched, crews can be evacuated. The environment is hostile, but access is possible. Timing matters, but response is feasible. In the deep ocean, rescue at extreme depth is essentially impossible. No fleet of standby submersibles exists. No rapid response system can reach kilometers below the surface in time. Even locating a disabled vehicle precisely is difficult. By the time help could arrive, the situation would already be resolved one way or another. Space also offers predictability. Vacuum behaves consistently. Radiation levels can be measured and anticipated. Orbital mechanics are stable and calculable. Space weather can disrupt systems, but it follows known patterns. The deep ocean is less predictable. Currents shift, sediment moves, equipment can be buried unexpectedly. The seafloor is uneven and unstable. Pressure remains constant, but the environment around a vessel can change subtly and suddenly. Then there is corrosion. Salt water is aggressive. It infiltrates. It reacts. It degrades materials over time. Even the best alloys eventually show wear. Seals fail. Connectors corrode. Maintenance becomes a constant battle. In space, corrosion is minimal. There is no moisture. Components age, but the environment does not actively attack them in the same way. Light behaves differently too. In space, sunlight is abundant. Solar power is reliable. Energy generation is relatively simple. In the deep ocean, sunlight disappears within the first few hundred meters. Power must be stored, generated chemically, or transmitted via cables. Every option adds complexity and risk. Psychologically, the environments differ in subtle but important ways. Astronauts can look out a window and see Earth. They can orient themselves. They can experience a sense of motion and perspective. The deep ocean offers no such reference. Outside the viewport is darkness. Not empty darkness, but close, heavy darkness. The sense of enclosure is more intense. Space feels open. The ocean feels closing. This matters for human endurance. Claustrophobia, stress, and sensory deprivation become more pronounced in environments where the outside feels pressing rather than distant. There is also the matter of familiarity. Humans evolved under a sky, not beneath kilometers of water. Our intuition about movement, sound, and space aligns better with open environments than enclosed ones. Even astronauts, despite the danger, often describe space as serene. Deep-sea explorers rarely use that word. From a logistical standpoint, space benefits from visibility and infrastructure. Satellites, tracking stations, launch facilities, and established orbits create a network of support. The deep ocean lacks this. Each mission starts almost from scratch. There are no permanent bases at depth, no refueling stations, no safe harbours. Cost also plays a role. Launching a spacecraft is expensive, but costs decrease with reuse and standardisation. Deep-sea vessels are custom-built, specialised, and used infrequently. There is little opportunity to amortise development costs across many missions. Each dive carries enormous expense. All of this leads to a counterintuitive reality. Space, while extreme, is an environment humans can isolate themselves from relatively cleanly. The deep ocean resists isolation. It presses in physically, chemically, and psychologically. That resistance is why human presence at depth remains brief and rare. It is not a lack of ambition. It is a recognition that the ocean does not simply surround you. It participates in your failure if given the slightest opportunity. And this hostility becomes even clearer when we look at what happens not just to people, but to the machines we send in their place. Because even when humans stay safely at the surface, the ocean continues to test every bolt, seal, and circuit we lower into its depths. Going down is only half the journey. Coming back up is where most of the problems quietly wait. At a distance, descent into the deep ocean feels like the dangerous part. Pressure increases, light fades, systems strain, and the environment grows steadily more hostile. It feels intuitive to assume that once a vessel reaches the bottom and survives, the hardest work is done. In reality, reaching extreme depth is often the simpler phase. The return is where complexity compounds. The ocean does not treat descent and ascent as symmetrical experiences. Physics does not rewind itself just because a vehicle changes direction. Materials behave differently. Systems respond differently. Time works against you in subtle ways, and the margin for error becomes thinner the longer the journey lasts. When a submersible descends, it does so gradually. Weight is added, or buoyancy is reduced in controlled increments. Ballast systems release slowly. Pressure increases predictably. Engineers expect this. They design for it. The vessel settles into the environment as it sinks, adjusting to the growing load. At depth, everything stabilizes. Pressure is immense but constant. Temperature is low but steady. The vehicle reaches an equilibrium with its surroundings. In many ways, this is the calmest phase of the mission. Ascent breaks that equilibrium. To rise, a submersible must become buoyant again. This usually involves releasing ballast, often steel weights designed to fall away permanently. Once released, they cannot be recovered. The ascent becomes a one-way commitment. There is no pause button, no ability to hover indefinitely while reconsidering. As the vessel rises, pressure decreases. This sounds like relief, but it introduces its own dangers. Materials that were compressed begin to expand. Seals relax. Components shift. Tiny deformations that were harmless under compression can turn into leaks or misalignments as forces reverse. This transition phase is where systems are most vulnerable. If a hull was slightly deformed under pressure, it may not return perfectly to its original shape. Stress redistributes. Microscopic cracks can propagate. Fasteners loosen. Interfaces that were tight become imperfect. The vessel must survive not just the pressure at depth, but the mechanical fatigue of changing pressure over hours. The ascent is also long, very long. Rising from extreme depth cannot be rushed. Ascending too quickly creates pressure differentials that can damage the vessel and its occupants. Even though the interior is maintained at constant pressure, the structure itself experiences changing loads. Engineers set strict ascent rates to avoid structural shock. This means hours spent rising slowly through darkness, unable to speed up even if something begins to go wrong. If a system fails during ascent, options are limited. Ballast may already be released, power reserves may be declining, communication delays persist, there is no safe depth to stop at, no halfway point where conditions suddenly improve. And unlike descent, ascent does not benefit from gravity. A vessel sinks naturally when made heavier. Rising requires precise control of buoyancy. That control depends on valves, tanks, release mechanisms and calculations that must all function correctly after enduring extreme pressure. If any part of that system fails, the consequences can go in either direction. A vessel can become too buoyant, rising too fast, risking structural damage or loss of control. Or it can fail to become buoyant enough, remaining trapped at depth with no way to generate lift. Both scenarios are dangerous. One is violent, the other is slow. There's also the issue of energy. Deep-sea missions rely on stored power. Batteries degrade in cold environments. Power consumption increases under load. During ascent, systems must remain active for extended periods. Life support, navigation, communication, and monitoring cannot shut down. If power runs low during ascent, choices must be made. Non-essential systems may be turned off. Comfort disappears, redundancy shrinks, the margin narrows. For unmanned vehicles, loss of power can mean loss of the vehicle and all collected data. For manned missions, it becomes a question of survival. Another factor complicates ascent further, the ocean itself. Currents vary with depth. A vessel ascending through kilometers of water passes through multiple layers, each moving differently. Lateral forces push and pull unpredictably. Orientation shifts. Navigation becomes abstract. There are no visual landmarks to guide movement. A tethered vehicle must manage cable tension that changes constantly as depth decreases. Slack can tangle. Tension can snap lines. Untethered vehicles must rely entirely on internal systems to maintain orientation and stability. Sediment stirred during descent can linger in the water column. As a vessel rises, it may pass through its own disturbed environment. Visibility drops. Sensors must compensate. Pilots or operators lose external reference points. Then there is the human factor. If people are aboard, ascent is a psychological test. The knowledge that the most dangerous phase is still unfolding weighs heavily. Fatigue sets in. Focus must be maintained for hours. Every unusual sound invites interpretation. Every delay feels longer than it is. Unlike spaceflight, where ascent and descent phases are brief and well-defined, deep-sea ascent is prolonged uncertainty. There is no moment where danger clearly ends, only a slow easing that is not confirmed until the vessel breaches the surface. Even after surfacing, risks remain. Recovery operations must proceed carefully. Sudden exposure to surface conditions can stress materials. Handling heavy, pressure-fatigued vessels is complex. Damage that occurred during ascent may not be visible immediately. This is one reason deep-sea missions are so rare. Every descent commits not just to reaching depth, but to surviving a complete pressure cycle. Down, stabilize, up. Each phase carries risk, but ascent compounds all previous stress into a final test. It is also why permanent presence at extreme depth is so impractical. Living systems require regular movement, resupply, maintenance, and emergency evacuation capability. All of those depend on safe ascent. If ascent is inherently dangerous even under ideal conditions, building routine operations around it becomes unrealistic. The problem with going down and coming back up is not just mechanical, it is structural, it is systemic. It reveals that extreme depth is not a place humans can interact with casually. Every visit is a closed loop with no shortcuts. This reality has pushed exploration increasingly toward machines rather than people. Vehicles that can be abandoned if necessary. Instruments that do not require return. Sensors that transmit data without needing recovery. But even machines struggle. As the focus shifts from the journey itself to the tools we trust to make it, a pattern emerges. Often, it is not the ocean that gives up first. It is the technology we send into it. Steel and glass feel permanent to us. They define skylines, bridges, vehicles, and cities. They give shape to the modern world. When humans want to go somewhere dangerous, they wrap themselves in metal and transparency and trust that it will hold. Most of the time, that trust is well placed. On land, in air, even in orbit, steel and glass are symbols of confidence. They suggest control. In the deepest ocean, they become reminders of limitation. Human engineering has always been about creating stable spaces inside unstable environments. We build walls to hold back weather, hulls to hold back water, cabins to hold back vacuum. The idea is simple: separate the inside from the outside, maintain conditions where the human body can function. Everything else becomes a problem of materials, geometry, and precision. The Mariana Trench tests that idea more aggressively than almost any other place on Earth. Steel, for all its strength, is not invincible. It has limits defined not by how hard it is, but by how it behaves under continuous uniform compression. At extreme depth, steel does not crack the way it might under impact. It yields, it bends, it slowly changes shape under stress. Even alloys designed for pressure resistance experience microscopic deformation when subjected to thousands of atmospheres. This deformation is not dramatic. It is not visible to the naked eye. But over time it matters. Pressure does not need to break steel outright to defeat it. It only needs to push it slightly out of tolerance. Submersible hulls are often built as thick spheres or cylinders made from forged steel or titanium. The forging process itself is critical. Cast metal can contain tiny voids or inconsistencies that act as weak points under compression. Forged metal is denser and more uniform. Even then, engineers must assume that no piece of metal is perfect. Every hull is inspected using ultrasound, X-rays, and other non-destructive testing methods. Every weld is scrutinized. Every surface is measured. The margin between safe and unsafe is not large enough to allow optimism. Glass presents an even greater challenge. In everyday life, glass feels fragile. At depth, it must be anything but. Windows on deep-sea submersibles are not thin panes. They are massive blocks, often made of acrylic rather than traditional glass, shaped into thick domes. Acrylic behaves differently under pressure. It compresses slightly rather than shattering. That flexibility is its advantage. Still, even these windows are among the most stressed components of any deep-diving vessel. They must remain optically clear while bearing immense load. They must seal perfectly against metal interfaces that expand and contract differently under temperature and pressure changes. A mismatch of micrometers can create stress concentrations. At extreme depth, a window does not just allow observation. It becomes a liability that must be justified. Some modern submersibles reduce or eliminate windows entirely, relying on cameras instead. This is not because engineers dislike windows, but because each opening in a pressure hull is a compromise. Every penetration is a risk. The fewer there are, the better. Then there are seals. Rubber and synthetic polymers that function reliably at the surface behave very differently under pressure. They compress. They stiffen. They can extrude from their grooves. Seals that are perfectly tight at one pressure may leak at another. Engineers must design sealing systems that work across enormous pressure ranges without failure. This is one of the quiet limits of human engineering. Seals are not glamorous. They do not attract attention. But they are often the first point of failure. A leak does not need to be dramatic to be deadly. A slow ingress of water can short electronics, compromise buoyancy, and cascade into larger failures. Electronics themselves pose another challenge. Modern exploration relies on sensors, processors, and communication systems that are delicate by nature. Silicon chips do not appreciate being compressed. Solder joints fatigue, connectors loosen. Even when electronics are housed inside pressure-resistant containers, those containers experience stress that can be transmitted inward. Thermal management becomes difficult. Heat generated by electronics has nowhere to go in cold, high-pressure environments. Insulation traps heat. Conductive paths change under compression. Systems that operate comfortably at the surface overheat or shut down at depth. Power systems suffer as well. Batteries lose efficiency in cold environments. Chemical reactions slow. Internal resistance increases. Delivering consistent power becomes harder just as demand increases. Cables are another weak link. Whether used for power, data, or recovery, cables descending into extreme depth face conflicting requirements. They must be strong enough to support their own weight over kilometers, flexible enough to handle motion, resistant to crushing, resistant to corrosion, electrically reliable. No single material excels at all of these simultaneously. Compromises are inevitable. Engineers design around them, but they cannot eliminate them. Even small design decisions become critical. The shape of a bolt head, the radius of a corner, the finish of a surface. Under pressure, stress concentrates at imperfections. Sharp edges amplify force. Smooth curves distribute it. This is why deep-sea engineering appears conservative compared to other fields. Designs look simple, rounded, overbuilt. Innovation is incremental. Novel shapes are avoided. Proven solutions are favoured. It is not because engineers lack creativity. It is because the environment punishes novelty. Material science has advanced dramatically in recent decades. New alloys, composites, ceramics. Yet very few of these materials make it into deep diving applications. Many are strong in tension but weak in compression. Some are brittle. Others degrade in salt water. Some perform well initially but fail under repeated pressure cycles. The Mariana Trench does not allow trial and error. Each test is expensive. Each failure is total. There is no safe testing ground at partial depth that perfectly replicates conditions at full depth. Pressure scales linearly, but failure modes do not. Testing facilities exist that simulate extreme pressure using chambers filled with water or oil. These chambers are impressive, but they are still approximations. They cannot fully replicate the combined effects of pressure, cold, corrosion, and time. This leads to a fundamental limit. Human engineering excels at environments where failure can be observed, studied, and corrected iteratively. The deepest ocean allows very few iterations. Progress is slow by necessity. There is also the issue of scale. To resist pressure, structures must be thick. Thickness adds weight. Weight increases the difficulty of deployment and recovery. Larger vessels require more support infrastructure. Smaller vessels limit space for systems and people. Every design choice pushes against another constraint. There is no configuration that optimizes all variables. Space exploration benefits from modularity. Components can be launched separately and assembled. Deep-sea exploration does not allow this. Assembly at depth is not practical. Everything must be built, tested, and sealed before descent. Maintenance is similarly constrained. In space, astronauts perform repairs. Components are replaced. Systems are upgraded. At extreme depth, maintenance means retrieval. Retrieval means ascent. Ascent means risk. This is why permanent installations at extreme depth are not just difficult, but strategically unsound. Any structure placed there would degrade over time. Seals would age, materials would fatigue. Without regular maintenance, failure would be inevitable. With maintenance, repeated ascents and descents would introduce unacceptable risk. Human engineering also depends on standardization. Parts are mass-produced, processes are optimized. In deep-sea exploration, everything is bespoke, custom-built, one-off. There is no economy of scale. This limits progress not because solutions do not exist in theory, but because implementing them repeatedly is not feasible. The ocean does not reward ambition the way space sometimes does. It does not allow incremental expansion of capability. Each increase in depth requires disproportionate increases in cost, complexity, and risk. Steel and glass can take us a long way. They can hold back immense forces for limited periods. They can create brief islands of habitability in hostile environments. But the Mariana Trench exposes the point where those materials stop being enablers and start being constraints. They do not fail because they are weak. They fail because the environment demands perfection, and perfection is not something engineering can guarantee indefinitely. As exploration continues, attention increasingly turns away from putting humans inside pressure hulls and towards sending machines alone. Systems that do not require windows, that do not require air, that do not care about comfort or psychology. Even then, those machines fail, and when they do, the ocean does not give them back easily. Because steel and glass are only as strong as the assumptions behind them, and the deep ocean has a way of revealing which assumptions were wrong. Machines do not panic. They do not feel fear, anticipation, or doubt. They follow instructions, execute code, and respond to physical inputs exactly as designed. And yet, in the deepest parts of the ocean, machines are often the first to fail. Not because they are poorly built, not because engineers overlooked something obvious, but because the environment quietly erodes certainty in ways that no checklist can fully anticipate. When humans began exploring extreme ocean depths more seriously, machines were seen as the solution. If pressure destroys the body, remove the body. If isolation overwhelms the mind, eliminate the need for one. If rescue is impossible, accept loss as part of the mission. Unmanned vehicles could go deeper, stay longer, and take risks that no human ever could. For a while, this worked. Robotic probes descended farther than any crewed vessel. Sensors mapped the seafloor. Cameras captured images from places no eyes had ever seen. Instruments sampled sediment, measured chemistry, and listened to the quiet movements of the deep. But over time, a pattern emerged. Machines did not fail spectacularly. They failed quietly, gradually, in ways that were difficult to diagnose and even harder to prevent. At extreme depth, nothing behaves exactly as expected. Electronics, which form the nervous system of any machine, are particularly vulnerable. Silicon chips are precise structures, etched at microscopic scales. Under high pressure, those scales matter. Compression changes distances between components. Solder joints experience stress they were never designed to endure. Over time, connections degrade. Even when electronics are housed inside pressure-resistant enclosures, they are not immune. The enclosures themselves flex. Not much, but enough. That flex transmits stress inward. Over hours and days, that stress accumulates. Then there is temperature. The deep ocean is cold, hovering just above freezing. Cold slows chemical reactions. Batteries lose efficiency. Voltage drops. Sensors drift out of calibration. Materials that expand and contract at predictable rates on the surface behave differently under sustained cold and pressure. Power management becomes a constant struggle. Machines must balance limited energy reserves against continuous demand. Every sensor turned on draws power. Every transmission costs energy. Every adjustment uses resources that cannot be replenished at depth. When power runs low, machines must make choices. Non-essential systems shut down. Redundancy disappears. A vehicle that began its mission robust and flexible becomes brittle and constrained. Navigation systems also suffer. In the absence of GPS, machines rely on inertial navigation, sonar and preloaded maps. Inertial systems drift over time. Sonar depends on sound propagation, which varies with temperature, salinity and pressure. Maps of the deep sea floor are often incomplete or outdated. A small navigation error near the surface is trivial. At depth, it can be fatal. A vehicle may descend onto an unexpected slope. It may land on unstable sediment. It may become trapped in soft seafloor material that behaves like mud rather than solid ground. When this happens, machines do not have intuition. They do not recognize danger unless sensors explicitly detect it. They cannot improvise solutions beyond their programming. Mechanical systems are equally vulnerable. Thrusters designed to operate smoothly at moderate depth struggle under extreme pressure. Bearings wear differently. Lubricants thicken. Seals stiffen. Motors draw more current to overcome resistance, increasing heat and accelerating power depletion. Articulated arms, used to collect samples or place instruments, become points of failure. Each joint is a potential leak. Each movement introduces stress. A stuck arm can unbalance a vehicle, making ascent difficult or impossible. Cameras face their own challenges. Housings must remain clear. Lenses must withstand pressure without distortion. Lighting systems must operate reliably in cold water for long periods. A single failed light can render visual data useless in complete darkness. Then there is communication. Unmanned vehicles often operate semi-autonomously, but they still depend on intermittent communication with the surface. Acoustic signals are slow and limited. Data packets are small. Commands may arrive late or not at all. If a machine encounters an unexpected situation, it cannot ask for clarification. It cannot describe ambiguity. It executes the best response available within its programming, even if that response is suboptimal. This is how machines blink first. Not with alarms or dramatic failures, but with silence, a mistransmission, a sensor that stops responding, a data stream that becomes corrupted. From the surface, it is often impossible to know what went wrong. Recovery is rarely an option. If a machine fails at extreme depth, retrieving it may be impossible or too risky to justify. The vehicle becomes part of the sea floor, another piece of debris in a place already littered with remnants of failed attempts. This loss is not just financial, it is informational. Data collected but not transmitted is lost. Instruments placed but not recovered cannot be recalibrated or reused. Each failure slows progress. Engineers learn from these losses, but learning is slow. There are few opportunities to test improvements. Each mission requires significant funding, planning, and time. Iteration cycles stretch across years. The deep ocean does not allow rapid prototyping. There is also the issue of longevity. Machines that perform well for a few hours or days at depth often fail when asked to remain longer. Corrosion works quietly. Microbial growth occurs even in cold, dark environments. Sediment accumulates, moving parts seize. Long-term deployments reveal weaknesses that short missions do not. Materials that survive brief exposure degrade under sustained conditions. Designs that appear robust fail slowly. Autonomous vehicles face an additional challenge. Decision-making in unpredictable environments is difficult even with advanced algorithms. The deep ocean presents scenarios that are poorly represented in training data. Slopes collapse, currents shift, objects appear that were not mapped. When autonomy fails, the machine does not know that it has failed. It continues executing flawed logic until resources are exhausted. There have been missions where vehicles descended successfully, completed tasks, and then failed to ascend. A valve didn't open. A ballast release mechanism jammed. A power system shut down prematurely. From the surface, operators waited. Signals did not return. The ocean remained silent. In some cases, machines were later found years or decades afterward, resting quietly on the seafloor, intact but inert. Their missions ended not with destruction, but with abandonment. These failures highlight a deeper truth. Machines remove human vulnerability, but they do not remove environmental hostility. They simply shift the point of failure. The deep ocean exploits complexity. The more systems a machine has, the more opportunities there are for something to go wrong. Simplifying designs reduces risk, but also limits capability. Adding redundancy increases reliability, but also increases weight, power consumption, and failure points. There is no perfect balance. Engineers constantly make trade-offs, more sensors or fewer, longer missions or safer margins, greater autonomy or stricter control. Every choice is a compromise shaped by an environment that does not adapt in return. The fact that machines blink first is not a condemnation of technology. It is a measure of the trench's consistency. The environment does not change to accommodate innovation. It remains exactly as it is, waiting for designs to meet its terms. In space, machines fail too, but failures are often visible. Debris orbits. Signals fade gradually. Repairs are sometimes possible. In the deep ocean, failure disappears downward. The evidence sinks into darkness. This invisibility complicates progress. Without clear feedback, diagnosing failure modes becomes difficult. Engineers must infer causes from partial data, simulations and assumptions. Despite this, machines remain our best tools for deep exploration. They go where humans cannot. They endure conditions no body could survive. They gather information that reshapes understanding of Earth's geology and biology. But they also reveal the limits of control. Every time a machine fails at depth, it reinforces the lesson that the ocean does not care about intention. It does not distinguish between manned and unmanned. It applies the same rules relentlessly. As technology advances, machines will improve, materials will strengthen, algorithms will adapt, missions will last longer. Yet even then, machines will continue to blink first, because they are still bound by physics, still vulnerable to pressure, cold, corrosion and isolation, still required to function perfectly in a place that tolerates no imperfection. And beyond the mechanical failures lies another barrier, one that machines do not experience directly, but that shapes every decision about sending them down. The recognition that when something goes wrong at extreme depth, help does not come. Rescue in the deepest parts of the ocean is not delayed, it is absent. The Challenger Deep does not announce itself as a destination. There is no sudden edge, no visible drop, no marker that says this is where the world ends. It is not a cliff in the way humans understand cliffs. It is a gradual surrender of depth, a slow slipping downward into a place where every familiar reference quietly disappears. It sits at the southern end of the Mariana Trench, deeper than any other measured point in Earth's oceans. A narrow depression within a larger depression, shaped not by erosion or collapse, but by immense tectonic forces pushing and folding the planet's crust over tens of millions of years. The Pacific Plate continues to slide beneath the Mariana Plate even now, millimetre by millimetre, quietly deepening a place that already feels excessive. What makes the Challenger Deep different from other extreme environments is not just that it is deep, but that it concentrates every hostile factor the ocean can offer into one location. Pressure reaches its maximum. Darkness is total. Temperature is near freezing. The seafloor is unstable. Communication is strained. And the margin for survival narrows to almost nothing. This is why it has been visited so rarely. Descending into the Challenger Deep is not like travelling to a remote region. It is more like entering a zone where the rules governing ordinary exploration no longer apply. Every assumption must be re-examined. Every system must perform exactly as intended, not just once, but continuously, for the entire duration of the mission. At that depth, pressure exceeds 1,000 atmospheres. This is not simply a larger number than elsewhere in the trench, it is a qualitative change. The forces involved are so extreme that even pressure-resistant vessels are operating near the upper limits of what materials science can reliably support. A pressure hull at Challenger Deep is not merely strong, it is burdened. It is under constant load, with no variation, no release, no moment of rest. The structure is being compressed relentlessly, its molecules pushed closer together than they were ever meant to be. Engineers calculate these forces carefully, but calculations do not eliminate uncertainty. They only define its boundaries. The seafloor itself offers no comfort. Unlike continental shelves or mid-ocean plains, the bottom of the Challenger Deep is composed largely of fine sediment. This sediment behaves more like thick powder than solid ground. When disturbed, it forms clouds that can persist for hours. Visibility drops to nothing, instruments clog, vehicles lose reference points. Landing on this surface is delicate. Too much force, and a vehicle sinks unevenly. Too little control, and it may tilt or roll. Once settled, movement becomes risky. Thrusters stir sediment, arms displace material. Every action has unintended consequences, and yet life exists there. Small crustaceans, fish, and microorganisms have been observed at these depths. Their presence is not dramatic, but it is profound. They move slowly. They conserve energy. Their bodies are adapted to pressure in ways that defy human intuition. Bones are flexible or reduced. Cell membranes function under compression. Enzymes operate efficiently in cold and darkness. These organisms do not experience the Challenger Deep as hostile. It is simply home. For humans and machines, it is something else entirely. Sound behaves strangely at these depths. Pressure affects water density, which in turn alters how sound waves travel. Echoes can be misleading. Distances feel compressed or expanded depending on conditions. Sonar readings require careful interpretation. A misjudgment of meters can mean collision or entrapment. Time stretches in unexpected ways. A descent to the Challenger Deep can take several hours. During that time, there is nothing to see outside the viewport except darkness. No passing features. No visual confirmation of progress. Instruments provide numbers, but numbers lack narrative. The sense of motion becomes abstract. At the bottom, time feels suspended. Not because it stops, but because nothing changes. There is no day or night cycle, no weather, no visible movement except what the vehicle itself introduces. The environment feels indifferent, not actively threatening, but utterly uninterested. This indifference is part of what makes the Challenger Deep unforgiving. There is no margin granted for human error. The environment does not accommodate adaptation. It does not soften its conditions in response to presence. It does not reward persistence. If a system fails here, there is no alternative mode of operation, no fallback environment that is merely uncomfortable instead of lethal. Failure means the environment instantly reasserts itself. The Challenger Deep has no tolerance for partial success. Even the act of measuring depth is complex. Water pressure deforms instruments. Acoustic signals refract. Tidal forces subtly alter readings. Estimates of maximum depth have changed over time as measurement techniques improved. The numbers differ by tens of meters depending on methodology. This uncertainty matters. When operating near structural limits, knowing the exact depth is not academic. It defines whether a vessel remains within its design envelope or crosses it. Every descent into the Challenger Deep is therefore an act of trust. Trust in models, trust in materials, trust in calculations performed far from the environment they describe. And once there, trust must persist. The Challenger Deep does not allow constant adjustment. Thrusters cannot compensate endlessly. Power must be conserved. Movements must be deliberate. Each action increases wear, consumes energy, and introduces risk. This is why missions to the Challenger Deep are brief. Time at the bottom is measured in minutes or hours, not days. Data collection is prioritized. Redundancy is minimal. There is no lingering. The return begins almost immediately. The ascent from the Challenger Deep is psychologically heavy. It is not a moment of relief, but of continued vigilance. The vessel must survive a complete reversal of pressure, passing through every stress level again in the opposite direction. Components that endured compression must now endure relaxation. Seals must remain tight. Structures must remain aligned. Only when the surface is breached does danger begin to recede. Even then, it does not vanish instantly. What gives the Challenger Deep its reputation as a place without mercy is not that it destroys indiscriminately, but that it makes no exceptions. It treats all intrusions equally. Human ambition, technological sophistication, and careful planning do not change its conditions. There is no negotiation with depth. This is why there are no permanent markers at the bottom, no structures, no cables connecting it to the surface, no stations. Each visit leaves almost no trace. The sediment settles. The water returns to stillness. The trench continues as it always has, in contrast to space where human presence leaves lasting artifacts. The deep ocean absorbs and erases. Even large objects can disappear beneath sediment over time. Wreckage becomes part of the landscape. Evidence fades. This erasure reinforces the sense that the Challenger Deep is not meant to be occupied, only observed briefly and cautiously. The place does not invite exploration in the way other frontiers do. It does not suggest progress through repeated visitation. It suggests restraint. As technology advances, the Challenger Deep remains a reference point, a benchmark against which capability is measured. A reminder that there are environments where improvement slows not because of lack of effort, but because of fundamental constraints. The Challenger Deep does not represent a failure of exploration. It represents a boundary condition, a place that defines what's possible by showing what is not sustainable. It is tempting to frame such places as challenges to be overcome, but that framing assumes that all barriers exist to be crossed. Some exist to delineate. The Challenger Deep delineates the point at which Earth's own environment becomes incompatible with long-term human presence. And yet, curiosity persists. Every generation returns to this place with new tools, new materials, new ideas. Each visit adds data. Each descent refines understanding. Progress is real, but it is slow and careful. The Challenger Deep allows knowledge, but not comfort. Observation, but not habitation. Contact, but not familiarity. It is a place without mercy because mercy implies discretion. The deep ocean has none. It applies pressure equally, darkness fully, isolation completely. And still, we return. Not because we expect it to change, but because understanding where the limits lie is part of understanding ourselves. As exploration continues beyond this point, attention begins to shift away from the environment itself and toward the strange fact that life thrives here in ways humans cannot. And that contrast raises a quiet question. If the Challenger Deep allows life, but not us, what exactly is it that life has learned to do differently? Life does not arrive at the deepest parts of the ocean by accident. It does not drift there unprepared, or stumble into the Challenger Deep and somehow endure out of luck. The organisms that exist at those depths are the result of slow, relentless adaptation to conditions that humans experience only briefly and through layers of protection. They are not visitors, they are residents, and their presence challenges one of our most persistent assumptions, that extreme environments are empty unless humans make them otherwise. At first it seems impossible. Pressure that would crush steel, darkness that has never known sunlight, temperatures that hover just above freezing, a landscape where food is scarce and energy arrives slowly, unpredictably, and often in forms that would be toxic to surface life. And yet, not only does life exist there, it functions with quiet efficiency. The difference begins at the most fundamental level. Human bodies are built around resistance. We maintain internal pressure against external pressure. We rely on rigid structures, bones, organs, air-filled spaces. These features serve us well on land and at shallow depths, but they become liabilities as pressure increases. The deeper we go, the harder we must work to preserve the difference between inside and outside. Deep-sea life takes the opposite approach. Instead of resisting pressure, it accepts it. Many organisms at extreme depth have bodies that are soft, flexible, and compressible. They do not maintain large internal cavities filled with gas. Their tissues are structured to function while compressed. Pressure passes through them rather than collapsing them. This is not strength in the human sense, it is compatibility. At the cellular level, these organisms have membranes that remain stable under pressure. The molecules that make up those membranes are arranged differently, allowing them to remain fluid even when compressed. Enzymes, the proteins that drive chemical reactions in cells, are adapted to function efficiently in cold, high-pressure environments. Reactions that would slow to a crawl in surface organisms continue steadily in the deep. Human enzymes, by contrast, are tuned to a narrow range of conditions. Deviate too far and they lose their shape, lose their function. Cells fail. Deep-sea organisms also handle oxygen differently. Oxygen is scarce at depth, but many creatures have adapted to survive with extremely low concentrations. Their metabolisms run slowly. Energy is conserved. Movement is deliberate, not wasteful. Nothing is rushed because rushing would be unsustainable. This slow pace is not weakness. It is optimization. Food in the deepest ocean does not arrive regularly. There is no sunlight to support photosynthesis. Instead, energy enters the system in fragments, organic matter drifting down from above, chemical compounds released from the Earth's crust, occasional falls of larger material, a dead organism sinking from the surface, providing a brief abundance that may take years to arrive again. Life at depth has adapted to this uncertainty. Some organisms can go long periods without feeding, others specialize in scavenging. Some rely on symbiotic relationships with bacteria that can metabolize chemicals like methane or hydrogen sulfide. These bacteria convert chemical energy into forms their hosts can use. Humans have no equivalent system. We require regular intake of food, oxygen, and heat. Interrupt those flows, and survival time is measured in hours or days. Pressure also influences reproduction. Many deep-sea organisms reproduce slowly. Development takes time. Growth is measured in years, not weeks. This is a response to limited energy availability and stable environmental conditions. There is no advantage to rapid reproduction when resources cannot support it. This slow life cycle contrasts sharply with human biology, which depends on relatively fast growth, frequent reproduction, and high energy throughput. The deep ocean does not support that strategy. Another difference lies in sensory systems. In darkness, vision becomes less useful. Many deep-sea organisms have reduced or absent eyes. Others have eyes adapted to detect faint bioluminescent signals rather than reflected light. Some rely more on chemical sensing or vibration detection. They feel their environment rather than seeing it. Humans depend heavily on vision. In the deep ocean, vision must be manufactured through artificial light and cameras. Without them, we are nearly blind. Bioluminescence is common at depth. Some organisms produce light through chemical reactions, using it to attract prey, deter predators, or communicate. This light is not decorative. It is functional. It operates at wavelengths suited to the environment. It is efficient. Humans, when they bring light to the deep ocean, flood it with intensity. Artificial lights are bright, power-hungry, and disruptive. They reveal, but they also disturb. Creatures adapted to darkness react differently to sudden illumination. Some flee, some freeze, some are damaged. Even our presence alters the environment. Deep-sea organisms are adapted to stillness. Water movement at extreme depth is slow. Disturbances persist longer. When a submersible descends, it creates currents, noise, and sediment clouds. These changes can affect local organisms for hours or days. The environment does not immediately reset. This matters because it highlights how foreign human activity remains, even when no direct harm is intended. Perhaps the most striking difference between deep-sea life and humans lies in resilience. Deep-sea organisms tolerate conditions that would be lethal to surface life, but they are often fragile in other ways. Many cannot survive changes in pressure. Bring them to the surface too quickly and they die. Their bodies are not designed for low pressure. They cannot maintain structure when compression is removed. In this sense, they are as bound to their environment as humans are to ours. This mutual exclusivity is important. It means that the deep ocean is not simply a harsher version of the surface. It is a fundamentally different regime. Life there is not stronger or weaker in absolute terms. It is specialized. Humans could not evolve to live there without becoming something else entirely. This reality complicates the idea of colonization. We often imagine that if life exists somewhere, humans can eventually join it, build habitats, engineer solutions, adapt technology. But deep-sea life shows that adaptation is not just about protection. It is about integration. Life at depth does not isolate itself from pressure. It incorporates pressure into its functioning. It does not fight darkness. It uses it. It does not demand frequent energy input. It slows down. For humans, slowing down is not enough. Our biology, psychology, and social structures depend on conditions that the deep ocean does not provide. There is also an evolutionary timescale problem. The adaptations seen in deep-sea organisms occurred over millions of years. Small changes accumulated slowly, guided by selection pressures that rewarded compatibility with the environment. Human engineering operates on timescales of decades. We build solutions quickly, test them, iterate. That approach works well where environments are forgiving enough to allow iteration. The Mariana Trench does not allow that luxury. Every test is expensive. Every failure is final. There is no rapid evolutionary process for technology in this context. Progress must be cautious, conservative, and incremental. This is why, despite knowing that life thrives at depth, humans do not take that as an invitation. It is not a proof of accessibility. It is a proof of difference. There is also an ethical dimension. Deep-sea ecosystems are among the least disturbed on Earth. Their slow pace of life makes them particularly vulnerable to disruption. Damage that might heal quickly in shallow ecosystems can persist for decades or centuries at depth. Sediment disturbance, chemical contamination, and physical damage do not disappear quickly. As interest grows in deep-sea mining and resource extraction, this vulnerability becomes more concerning. These same conditions that make the environment hostile to humans make it fragile in its own way. Recovery is slow, baselines are poorly understood, understanding that life thrives where humans cannot invites humility. It suggests that absence of human presence does not imply emptiness. It challenges the idea that exploration must always lead to occupation. The deep ocean does not need us. It does not benefit from our arrival. Our interest in it is driven by curiosity, knowledge, and sometimes utility, not mutual dependence. This perspective reframes the question of why humans cannot go deeper. It is not simply that the environment is too harsh, it is that it is already full, just not with us. The Challenger Deep is not a void waiting to be filled. It is a system already operating according to rules that do not include human participation. As we learn more about these systems, the contrast becomes sharper. The more we understand how life thrives at depth, the clearer it becomes why humans struggle to remain there. The problem is not a lack of technology alone, it is a mismatch of strategies. Deep-sea life survives by yielding to the environment. Humans survive by controlling it. At some point, control becomes impractical. This realization does not end exploration. It reshapes it. It shifts focus from presence to observation, from occupation to understanding, from conquering depth to respecting it. And as attention turns from biology to perception, another barrier comes into view, one that affects humans more than machines, one that operates even when systems function perfectly. The deep ocean is not just physically hostile, it is sensorially empty in ways the human mind is not well equipped to handle. And in that emptiness, something subtle begins to happen. Darkness in the deep ocean is not the same darkness people experience at night on land. It is not the absence of sunlight followed by moonlight, streetlights, or distant glow. It is not a dimming that invites adjustment. It is not something eyes gradually learn to work with. It is a condition that removes reference entirely. Once sunlight disappears, it does not partially return. There is no horizon, no sky, no sense of distance created by shadow or contrast. There is only blackness that remains constant regardless of time, movement, or attention. For humans, this kind of darkness is deeply unsettling, not because it is frightening in a dramatic sense, but because it deprives the brain of the information it depends on to orient itself. Vision is not just about seeing objects. It is how the brain constructs space, direction, and stability. When vision is removed completely, the mind begins to lose its anchor. In the upper layers of the ocean, darkness increases gradually. Light fades, colours disappear, and shapes become less defined. By a few hundred meters, the sun no longer penetrates. Beyond that point, the environment does not grow darker. It is simply dark, permanently and uniformly. At the depth of the Challenger Deep, there has been no natural light for millions of years. Any illumination that exists comes from two sources. The first is bioluminescence, brief and localized flashes produced by organisms. The second is artificial light carried down by human technology. Both are temporary, neither provides context. Artificial lights reveal only what they touch. A narrow cone of seafloor, a drifting particle, the edge of a rock. Everything beyond the beam remains invisible. The illuminated area feels disconnected from any larger environment, like standing in a dark room with a flashlight that never reaches the walls. This fragmented visibility disrupts perception. Humans rely on peripheral vision to maintain balance and orientation. In the deep ocean, peripheral vision provides no information. The brain receives input only from what is directly illuminated. Movement outside that zone does not exist perceptually. Distance becomes difficult to judge. Scale becomes ambiguous. Objects appear suddenly when they enter the beam. They vanish just as abruptly when they leave it. There is no gradual approach or departure. This unpredictability forces the brain into a constant state of vigilance. Even when nothing moves, the mind fills the silence. In darkness without reference, the brain searches for patterns. It invents motion. It misinterprets noise. A small vibration becomes meaningful. A minor shift in light becomes suspect. This is not imagination in a fictional sense. It is a neurological response to sensory deprivation. Studies of humans in dark, isolated environments consistently show similar effects. Time perception distorts, attention fluctuates, thoughts loop, minor concerns grow disproportionately large. The mind, deprived of external input, turns inward. In the deep ocean, this inward turn is amplified by the knowledge that the environment is actively hostile. Darkness is not just absence, it conceals pressure, isolation, and distance. The brain cannot separate the lack of visual information from the presence of danger. Unlike space, where darkness often comes with a view of stars or Earth, the deep ocean offers nothing comparable. There is no distant reference point, no fixed object to confirm orientation, no sense of movement relative to a larger frame. This lack of reference complicates even basic tasks. Pilots of submersibles rely heavily on instruments to compensate for visual deprivation. Depth gauges, orientation indicators, sonar displays. These tools replace vision, but they require constant attention and interpretation. They do not offer intuitive understanding. They offer numbers and symbols. Trusting instruments over instinct is cognitively demanding. Humans evolved to trust what they see. In the deep ocean, what you see is insufficient. The brain must override its own preferences continuously. This sustained effort leads to fatigue. Fatigue in darkness is not always physical. It is cognitive. The effort required to maintain focus, interpret limited information, and suppress instinctive responses accumulates over time. Even short missions can feel longer than they are. Darkness also affects emotional regulation. Without visual cues to signal change, time feels suspended. There is no dawn or dusk, no progression. The environment feels static. This can produce a sense of stagnation, as if movement has stopped even when it has not. In such conditions, small deviations become magnified. A delay in communication feels longer. A minor system alert feels more urgent. The mind lacks external reassurance to counterbalance internal reactions. Artificial lighting, while necessary, introduces its own problems. Bright lights reflect off suspended particles, creating visual noise. Sediment stirred by the vehicle fills the water column with drifting debris. This can make it difficult to see even nearby objects. The environment appears to move when it is actually still. This effect is disorienting. The brain interprets particle motion as vehicle motion. Pilots may feel as though they are drifting or rotating when they are not. Correcting for perceived movement can introduce real movement, compounding the problem. Some submersibles reduce lighting intensity to minimize this effect. Others use carefully angled beams. All approaches involve compromise. There is no lighting solution that restores normal vision. Darkness also eliminates anticipation. On land, vision allows us to see what is coming. Obstacles, changes in terrain, approaching objects. In the deep ocean, nothing is visible until it is already close. This compresses reaction time. For machines, this is a technical challenge. For humans, it is psychological. The inability to anticipate visually creates a constant low-level stress. The brain remains alert, waiting for something to appear. Over time, this alertness becomes exhausting. Darkness also affects memory. Experiences in visually rich environments are encoded with spatial detail, landmarks, colours, relative positions. In the deep ocean, memory encoding is impoverished. Events blend together. Locations feel indistinct. Without visual anchors, recollection becomes vague. This has practical consequences. Pilots may struggle to remember exact positions. Operators reviewing footage may find it difficult to reconstruct sequences. The environment resists narrative. Even after returning to the surface, memories of time spent in extreme darkness often feel incomplete. People describe the experience as compressed, blurred, or oddly distant. This sensory deprivation is one reason missions to extreme depth are kept short. It is not just about mechanical risk, it is about human limits. Long-term exposure to darkness without reference is associated with psychological strain, mood changes, irritability, difficulty concentrating, altered sleep patterns. These effects are well documented in other isolated environments, such as submarines and polar research stations, but they are intensified in the deep ocean by the lack of external cues. Space missions address this with structured schedules, artificial day-night cycles, and visual access to Earth or space. Deep-sea missions cannot replicate these conditions effectively. The environment outside the vessel remains uniformly dark regardless of internal lighting. There is also the issue of scale. In darkness, objects lose their apparent size. A small rock close to the camera can appear large. A large formation farther away can appear small or not at all. Without contextual cues, the brain cannot reliably judge distance. This makes navigation challenging. It also complicates scientific observation. Measurements must rely on instruments rather than visual estimation. Errors can occur if data is misinterpreted. For human observers, this loss of scale contributes to a feeling of unreality. The environment does not behave as expected. Familiar rules do not apply. This cognitive mismatch increases stress. Darkness without reference also affects communication between crew members. Visual cues play a role in human interaction. Facial expressions, gestures, shared attention toward visible objects. In the confined, dimly lit interior of a submersible, these cues are limited. Communication becomes more verbal, more explicit, more effortful. This can slow decision-making. It can also amplify misunderstandings. In high-risk environments, even small communication delays matter. The deep ocean removes not only light, but many of the subtle signals humans rely on to coordinate and reassure one another. Bioluminescence, when encountered, provides brief relief. A flash of light from an organism can feel startling but grounding. It confirms that something is there, that life exists beyond the hull. But these flashes are fleeting. They do not illuminate surroundings. They do not provide orientation. They vanish as quickly as they appear. In some cases, bioluminescent responses are triggered by disturbance. A vehicle moving through water may cause organisms to emit light. This creates the illusion of movement and activity, but it is a reaction, not an environment. Once the disturbance passes, darkness returns. For humans accustomed to visual richness, this repeated return to darkness reinforces the sense of isolation. The environment feels unresponsive. It does not acknowledge presence. This indifference is harder to tolerate than overt hostility. Hostile environments on land or in space often provide feedback. Wind, heat, radiation, visual cues of danger. The deep ocean offers silence and absence. Problems do not announce themselves visually. Failures are not immediately apparent. This makes vigilance harder to sustain. The brain wants cues. It wants confirmation. In darkness without reference, confirmation is rare. Machines do not experience this discomfort, but their operators do. Decisions made at the surface are influenced by how humans anticipate conditions below. Knowing that the environment will provide no visual reassurance affects risk assessment. It discourages prolonged missions. It favors automation. It pushes design toward minimizing human presence. Even when technology functions perfectly, the sensory environment remains hostile. This is an important distinction. Engineering can address pressure, temperature, and corrosion to a degree. It cannot easily address perception. Human sensory systems are fixed by biology. Adapting humans to darkness without reference would require altering fundamental aspects of cognition and perception. That is not an engineering problem. It is an evolutionary one. This reality places a soft but firm boundary on how humans interact with extreme depth. Even if structures could be made safe indefinitely, the sensory cost would remain. The deep ocean does not offer relief from darkness. There are no transitions, no variation, no natural signals to mark time or progress. For exploration, this means that presence must remain temporary. Observation must be mediated. Data must be gathered and analysed away from the environment itself. As attention shifts from perception to consequence, another limitation becomes impossible to ignore. In a place where vision offers no warning and distance prevents intervention, the concept of rescue begins to lose meaning. And once rescue becomes theoretical rather than practical, every decision changes. Communication feels effortless at the surface. Voices travel instantly. Signals move invisibly through air. Messages bounce between satellites and towers without us ever noticing the machinery behind them. We expect responses. We expect clarity. We expect to be heard. In the deep ocean, those expectations quietly collapse. The abyss does not block communication aggressively. It dissolves it. It stretches it, thins it, and strips it of immediacy until what remains feels more like suggestion than connection. This breakdown is not a technical inconvenience. It is a defining feature of why humans cannot operate freely at extreme depth. The problem begins with physics. Radio waves, which carry nearly all modern communication, do not travel well through seawater. Even at relatively shallow depths, radio signals weaken rapidly. Salt water absorbs electromagnetic energy efficiently. The deeper you go, the worse it gets. By the time you reach even a few hundred meters, radio communication is essentially impossible. This means that the systems we rely on for instant contact simply stop working. To communicate underwater, we turn to sound. Sound travels far in water, farther than in air, and for centuries it has been the only viable option for long-distance underwater communication. Whales use it. Submarines use it. Deep-sea vehicles use it. But sound is not radio. Sound moves slowly. Roughly 1,500 meters per second in seawater, depending on conditions. That is fast in human terms, but slow compared to the speed of light. Over kilometers of depth, even simple messages take seconds to arrive. More complex data takes much longer. This delay changes the nature of interaction. There is no real-time conversation. There is no back-and-forth adjustment. A command is sent. Then there is waiting. Then a response arrives, possibly altered by interference or noise. By the time clarification is possible, the situation may have changed. Bandwidth is also severely limited. Acoustic communication can transmit only small amounts of data reliably. High-resolution video is impossible to stream. Even images are difficult. Most communication consists of compressed telemetry, basic commands, and status updates. This forces prioritization. Only the most critical information is sent. Everything else is stored on board, hoping the vehicle will return intact. Noise complicates matters further. The ocean is not quiet. Currents move. Sediment shifts. Marine life produces sound. Distant ship traffic generates low-frequency noise that travels enormous distances underwater. Earthquakes, storms, and even waves breaking far away contribute to a constant acoustic background. This noise interferes with communication signals. Messages can be distorted, delayed, or lost entirely. Error correction helps, but it adds delay and further reduces bandwidth. At extreme depth, communication becomes intermittent by nature. This intermittency has practical consequences. Operators at the surface cannot monitor systems continuously. They receive snapshots rather than streams. If something begins to fail between transmissions, they may not know until it is too late. For manned missions, this creates a profound sense of isolation. Even when communication is functioning, it is sparse. A message sent upward disappears into the water, followed by silence. The response, when it comes, feels delayed and distant. There is no sense of presence on the other end. This is not loneliness in the emotional sense. It is disconnection in the operational sense. The crew must function autonomously, trusting procedures rather than guidance. In emergencies, this limitation becomes critical. If a problem arises, there is no immediate consultation. There is no rapid troubleshooting with a team of experts. Decisions must be made on the spot based on training and judgment, without knowing whether support even received the last update. In spaceflight, communication delays exist, but they are predictable. In low Earth orbit, delays are negligible. Even on missions to Mars, delays are measured in minutes, and bandwidth is sufficient for detailed data exchange. In the deep ocean, delays are shorter, but unpredictability is greater. Signals can fail entirely without warning. A vehicle can be functionally isolated even when communication equipment is intact. For unmanned vehicles, communication breakdown is one of the most common causes of mission loss. A probe descends. It transmits normally for a while, then transmissions become irregular, then they stop. The vehicle may still be functioning perfectly, but without communication, it is effectively gone. Recovery may be attempted, but without precise location data, searching kilometers of seafloor is impractical. The ocean swallows silence quickly. Tethered vehicles offer an alternative. Cables can transmit power and data directly. This improves communication dramatically. But tethers introduce new problems. Cables must withstand immense pressure, their own weight, and constant movement. They can snag on terrain. They can tangle. They can break. A broken tether ends communication instantly and may also compromise recovery. At extreme depth, tether length becomes enormous. Managing that length safely is a major engineering challenge. Winches must be precise. Tension must be monitored constantly. Any miscalculation can lead to catastrophic failure. Wireless acoustic communication avoids these issues but sacrifices reliability and speed. There is no perfect solution. This communication breakdown also affects navigation. Without reliable communication, vehicles must rely more heavily on autonomy. They must make decisions without human input. This requires complex algorithms capable of handling uncertainty. But uncertainty at extreme depth is difficult to model. The environment is poorly mapped. Conditions change subtly. Unexpected obstacles appear. Autonomous systems perform well in structured environments. The deep ocean is not structured. It is irregular, incomplete, and unpredictable. When communication breaks down, autonomy becomes a liability as well as a necessity. Human psychology is affected too. Knowing that communication can fail changes behavior. Crews become more conservative. Operators hesitate to authorize risky maneuvers. Missions are shortened. Objectives are reduced. This caution is not irrational. It reflects an understanding that once communication is lost, control is lost. Communication also shapes trust. At the surface, teams rely on constant feedback. In the abyss, trust shifts inward. Crews must trust their vessel. Operators must trust their code. Engineers must trust that assumptions made months or years earlier remain valid under conditions no one can observe directly. This trust is fragile. A single unexplained communication loss can undermine confidence in an entire system. Investigations may take years, redesigns may follow, progress slows. The abyss enforces patience through silence. There is also a philosophical dimension to this breakdown. Human societies are built on communication, language, signals, shared understanding. We coordinate through constant exchange. The deep ocean resists this fundamentally. It isolates not just bodies, but information. In such an environment, human presence becomes less effective. Coordination becomes costly. Collective problem-solving becomes limited. This is why deep-sea exploration relies heavily on pre-planned procedures. There is little room for improvisation based on new information. Plans must assume communication gaps. Every mission becomes a controlled experiment with limited flexibility. Even when communication works, it is never comfortable. Acoustic messages sound distorted, delayed, mechanical. The human voice loses its familiarity. Conversations feel unnatural. The medium itself reminds participants of separation. This subtle discomfort adds to cognitive load. It reinforces isolation. It makes long missions harder to sustain. Over time, this communication barrier becomes one of the most significant constraints on human activity at depth. Not because it makes exploration impossible, but because it makes it inefficient and risky. The abyss does not cut communication entirely. It degrades it just enough to matter. It forces humans to operate without reassurance, without immediate feedback, without the safety net of collective awareness. And when communication breaks down completely, the situation becomes stark. There is no way to ask for help, no way to explain what is happening, no way to negotiate with distance. This reality shapes every decision about sending humans or machines into extreme depth. It favors systems that can function without oversight. It favors short missions. It favors retreat over persistence. Because in the abyss, silence is not neutral. Silence means separation, and separation, at extreme depth, is one step away from finality. As this becomes clear, another question begins to surface. If communication fails and rescue is unlikely, what happens when something goes wrong? What does help look like in a place where distance, pressure, and silence all work against it? That question leads inevitably to the hardest limitation of all. Rescue is a comforting idea. It sits quietly in the background of nearly every risky human activity. If something goes wrong, help comes. Maybe not immediately, maybe not easily, but eventually. On land, this assumption is so deeply ingrained that we rarely question it. In the air, emergency landings exist. In space, rescue missions are complex but conceivable. Even in remote polar regions, assistance can be mobilized with enough time. In the deepest parts of the ocean, that assumption does not hold. Rescue is not difficult in the abyss. It is nearly impossible, not because humans lack compassion or capability, but because the environment eliminates the conditions that make rescue meaningful in the first place. Distance, pressure, time, and uncertainty combine in a way that turns response into theory rather than action. To understand why, it helps to consider what rescue actually requires. Rescue depends on awareness. Someone must know that something has gone wrong. It depends on location. Someone must know where the problem is. It depends on access. Someone must be able to reach the site. And it depends on time. Someone must arrive before conditions become unsurvivable. In the deep ocean, each of these requirements is compromised. Awareness is fragile. Communication, as already seen, is unreliable. A loss of signal may indicate a minor technical issue or total failure. There is no immediate way to tell which. Surface teams may not know whether a vessel is intact, damaged, or destroyed. Silence does not communicate urgency. It only communicates absence. Location is uncertain. Even when a vehicle's last known position is recorded, ocean currents can move objects laterally during descent or ascent. The seafloor is vast, uneven, and poorly mapped at extreme depth. Searching even a small area can take enormous time. Access is the greatest barrier of all. Reaching extreme depth is not like driving to an accident site. It requires specialized vessels capable of surviving immense pressure. There are very few such vessels in existence, and fewer still that can be deployed quickly. They are not kept on standby. They require preparation, transport, testing, and coordination. Even if a suitable rescue-capable submersible existed nearby, descent alone would take hours. By the time it reached the target depth, conditions for survival would likely already be resolved one way or another. Time is unforgiving. At extreme depth, emergencies escalate quickly. Structural failures are instantaneous. Power failures cascade. Life support systems have limited endurance. There is no buffer period during which a rescue can be organised. The window for effective intervention is not hours or days. It is often minutes, if it exists at all. This is why rescue planning for deep-sea missions looks very different from rescue planning elsewhere. Instead of focusing on response, it focuses on prevention. Systems are designed to avoid failure rather than recover from it. Redundancy is built in where possible. Procedures are conservative. Missions are short. There is no expectation that rescue will save the day. Consider the logistics alone. A rescue mission would require precise knowledge of the disabled vessel's depth, orientation, and condition. It would require a rescue vehicle capable of matching depth and pressure safely. It would require the ability to physically interact with the disabled vessel, possibly attaching lines, transferring power, or retrieving occupants. All of this would need to happen in darkness, under immense pressure, with limited communication, and with no room for error. Even small manipulations at depth are difficult. Robotic arms struggle with fine control under pressure. Visibility is limited. Sediment clouds obscure targets. Attaching a cable or docking with a damaged vessel is a delicate task under ideal conditions. Under emergency conditions, it becomes extraordinarily risky. Then there is the question of ascent. Even if occupants could be transferred to a rescue vehicle, ascent would still take hours. Both vessels would need to survive the pressure cycle. Any damage incurred during rescue operations could compromise the return. In many scenarios, attempting rescue could increase overall risk rather than reduce it. This reality is reflected in how deep-sea missions are authorized. Crews are briefed on the fact that rescue is not an option. They accept that their safety depends entirely on the integrity of their vessel and the correctness of their decisions. This is not presented dramatically. It is presented factually. The ocean does not allow otherwise. Unmanned missions face similar limitations. When a robotic vehicle becomes unresponsive at depth, recovery efforts may be attempted, but they are often abandoned after initial searches. The cost, risk, and low probability of success make prolonged rescue impractical. This acceptance of loss is uncomfortable, but necessary. Without it, exploration would halt entirely. The impossibility of rescue also shapes design philosophy. Deep-sea vehicles are often built to fail safely rather than fail recoverably. Ballast systems are designed to release automatically if power is lost, allowing the vehicle to ascend passively. This works in many cases, but not all. If a vehicle becomes entangled or trapped in sediment, buoyancy alone cannot free it. There are no tow trucks in the abyss. Human rescue scenarios are even more constrained. Life support systems are finite. Oxygen supplies are limited. Carbon dioxide removal systems must function continuously. Any interruption shortens survival time dramatically. Surface teams cannot replenish these systems remotely. They cannot increase oxygen flow or remove waste gases. They can only wait and listen, hoping for a signal. This waiting is one of the most psychologically difficult aspects of deep-sea operations. Operators know that if communication is lost, there is nothing they can do. They monitor instruments. They replay procedures. They search for explanations. But action is limited. This helplessness contrasts sharply with rescue scenarios in other environments, where activity, even if frantic, feels purposeful. In the abyss, restraint replaces response. Weather adds another layer of difficulty. Rescue operations must occur from surface vessels. Storms, waves, and currents affect launch and recovery. Even if a rescue vehicle could reach depth, surface conditions might prevent deployment. The ocean does not coordinate its hazards. Multiple risk factors can align simultaneously. There is also the issue of scale. The area of the seafloor at extreme depth is vast. Searching it is slow. Sonar can help, but resolution is limited. Objects can be buried by sediment. Debris fields can be scattered. Finding a disabled vessel is not guaranteed even if its approximate location is known. This uncertainty makes rescue planning speculative. Scenarios multiply. Resources are stretched. Decisions become difficult to justify. The absence of rescue capability feeds back into mission planning. Because rescue is almost impossible, missions are designed to minimize exposure. Time at depth is limited. Objectives are prioritized. Redundancy is added where feasible, but not indefinitely. At some point, additional redundancy adds complexity that increases failure risk. There is no configuration that eliminates danger. This acceptance of irreducible risk is one of the clearest reasons humans do not go deeper. Exploration depends not only on bravery and technology, but on a social contract. Participants must believe that society has done everything reasonable to protect them. In the deepest ocean, that contract reaches its limit. Society can build strong vessels, it can train skilled crews, it can plan carefully, but it cannot promise rescue. This does not mean deep-sea explorers are reckless. On the contrary, they are among the most cautious professionals in any field. They understand the environment intimately, they respect its constraints. But respect does not change physics. The abyss does not offer second chances. It does not pause while humans mobilize. It does not adapt to emergency protocols. This is why the deep ocean remains a place of visits rather than stays, of brief contact rather than continuous presence, of observation rather than occupation. Rescue, as a concept, relies on proximity, speed, and accessibility. The Mariana Trench provides none of these. The deeper one goes, the more rescue transforms from a plan into a hope, and from a hope into a memory of how things work elsewhere. This realization shapes not only engineering decisions but ethical ones. Sending humans into environments where rescue is impossible demands justification beyond curiosity. It requires extraordinary value and extraordinary care. As technology advances, some barriers may soften, communication may improve, autonomy may become more reliable, materials may strengthen, but rescue will remain constrained by distance and pressure. The ocean does not shrink. Because of this, attention increasingly turns to the human cost of operating in such environments. Not just physical risk, but psychological burden. The knowledge that help cannot come alters perception, behavior, and stress. And this leads to another limitation that cannot be engineered away. Even if machines survive, communication holds, and pressure is resisted, the human mind must endure the awareness of absolute isolation. That awareness carries its own weight. The psychological cost of extreme depth begins long before a vessel ever leaves the surface. It starts in planning rooms, during briefings, in the quiet moments when risk is explained plainly and without embellishment. There is no dramatic language, no heroic framing, just facts, distance, pressure, isolation, the absence of rescue, the limits of communication. Everyone involved understands that once the descent begins, the environment will not offer reassurance. That understanding settles into the mind slowly. Humans are remarkably adaptable, but adaptation has limits. The deep ocean pushes against those limits not through chaos or violence, but through consistency. Nothing changes quickly, nothing responds, nothing acknowledges presence. The environment does not threaten, it simply exists, and in doing so, it places a continuous cognitive load on anyone entering it. One of the most significant psychological stresses is confinement. Deep-sea submersibles are small, they have to be. Spherical pressure hulls that can withstand immense pressure do not scale well. Every additional centimetre of interior space adds exponential stress to the structure. As a result, crewed vehicles are often barely large enough for their occupants to sit, sometimes without the ability to stand or fully stretch. This confinement is not temporary in the way an elevator ride or a small room is temporary. It persists for hours. There is no visual escape, no change in scenery beyond what instruments and screens provide. The body remains still while the mind stays alert. Claustrophobia is an obvious concern, but even individuals who do not consider themselves claustrophobic can experience discomfort. The lack of movement, the proximity of surfaces, and the knowledge that the space cannot be exited under any circumstance amplify sensations that would otherwise be manageable. There is also the issue of sensory monotony. The deep ocean offers little variation. Sounds are constant and mechanical. Lighting is artificial and unchanging. The temperature remains stable. The environment lacks the subtle fluctuations that humans unconsciously use to mark time and regulate mood. Without variation, attention drifts inward. This inward focus can be productive in short bursts. It allows for concentration. It sharpens awareness of systems and procedures. Over longer periods, it becomes draining. Thoughts repeat. Minor concerns grow. The mind searches for stimulation and finds none. Time perception begins to distort. Without external cues, minutes feel longer or shorter unpredictably. A task that takes 5 minutes may feel like 15. An hour may pass unnoticed. This distortion complicates scheduling and pacing. Crew members must rely on clocks rather than intuition, which adds another layer of cognitive effort. In extreme environments, this effort accumulates. Another psychological factor is the absence of natural reference points. On land, orientation is intuitive. Gravity provides a clear down. Vision provides a horizon. Even in unfamiliar environments, these references remain. In the deep ocean, orientation is abstract. Down is a number on a gauge. Direction is a vector on a screen. The body receives little confirmation. This disconnect between perception and reality can be unsettling. The brain expects certain feedback from movement and does not receive it. This mismatch requires constant correction, which is tiring. There is also the awareness of vulnerability. At depth, every sound carries meaning. A creak in the hull, a change in motor pitch, a brief alarm. Even when systems are functioning normally, the mind remains attuned to potential failure. This vigilance is necessary, but it is also stressful. Unlike environments where danger comes from external events such as storms or terrain, danger at depth is embedded in the environment itself. It cannot be avoided by waiting. It cannot be escaped by moving. It must be endured. This endurance demands emotional regulation. Fear is not the dominant emotion reported by deep-sea explorers. Instead, it is tension. A steady, low-level awareness that does not peak dramatically, but does not subside either. Managing this tension requires discipline and experience. Training helps. Crews are selected for emotional stability, problem-solving ability, and comfort with isolation. Simulations prepare them for confined spaces and limited communication. Procedures are rehearsed extensively to reduce uncertainty. But training cannot eliminate the psychological cost. It can only reduce surprises. Isolation compounds these effects. Communication delays and limitations mean that social support is attenuated. Messages from the surface arrive sporadically. Responses feel distant. Even when contact is maintained, it lacks immediacy. Conversations are brief and task-focused. This lack of casual interaction matters. Humans rely on informal communication to regulate stress. Small talk, humour, shared observation. At depth, these outlets are limited. Crew members must rely more heavily on each other. This intensifies interpersonal dynamics. Small misunderstandings can feel larger. Differences in coping styles become more pronounced. Cooperation is essential, but it requires effort. The interior of a submersible offers little privacy. There is no space to withdraw, no way to be alone. Emotional regulation must occur in shared space, which can be challenging. For unmanned missions, these psychological factors do not apply directly, but they influence decision-making at the surface. Operators who know they cannot intervene directly may experience anxiety or frustration. Watching data streams without being able to act creates a sense of helplessness. This sense of helplessness is a powerful psychological stressor. It arises from the combination of responsibility and lack of control. Operators are accountable for mission outcomes, but their ability to influence those outcomes diminishes with depth. When something goes wrong, options are limited. This dynamic can lead to conservative decision-making. Missions may be aborted earlier than planned. Objectives may be reduced. This caution is rational, but it reflects the psychological burden of operating in environments where intervention is constrained. Another aspect of the psychological cost is anticipation. Before descent, there is a period of waiting. Equipment is checked, conditions are assessed, the vessel is prepared. During this time, individuals are aware of what lies ahead. The mind rehearses scenarios. What if communication fails? What if a system behaves unexpectedly? What if ascent is delayed? This anticipatory stress can be more taxing than the descent itself. Once the descent begins, there is a sense of commitment. Options narrow, decisions become final. This can produce relief, but also resignation. The psychological state shifts from planning to endurance. After the mission, there is often a delayed response. Returning to the surface does not immediately release psychological tension. The body may be safe, but the mind remains alert. It takes time to adjust back to environments with normal sensory input and social interaction. Some individuals report difficulty sleeping after deep-sea missions. Others experience vivid recollections of confined spaces or darkness. These responses are not pathological. They are natural reactions to intense, unfamiliar conditions. Long-term psychological effects are less well studied, partly because so few people have experienced extreme depth. But parallels can be drawn from other isolated environments, such as submarines, polar stations, and space missions. These studies suggest that prolonged exposure to isolation, confinement, and sensory monotony can affect mood, cognition, and interpersonal relationships. Effects vary widely between individuals, but the risk increases with duration and intensity. This is another reason why missions to extreme depth remain short. The environment does not support gradual acclimatization. There is no way to spend extended periods adjusting psychologically. Each mission is a discrete event, with preparation and recovery phases. The psychological cost also influences public perception and institutional decision-making. Organizations responsible for authorizing missions must consider not only technical risk, but human welfare. Sending people into environments with known psychological stresses and minimal rescue options raises ethical questions. Is the scientific value sufficient to justify the risk? Are there alternative methods that reduce human exposure? Can machines accomplish the same objectives? These questions are not abstract. They shape funding decisions, mission design, and operational protocols. Over time, the balance has shifted toward minimizing human presence at extreme depth. Machines can endure isolation without psychological cost. They can operate in darkness without distress. They can fail without trauma. Humans, by contrast, carry the experience with them. This does not mean that humans are incapable of deep-sea exploration. It means that such exploration exacts a cost that cannot be measured solely in equipment loss or mission success. It affects individuals, teams, and institutions. The deep ocean challenges not just physical endurance, but mental resilience. It asks people to function in environments that strip away many of the cues and comforts that support human cognition. It demands trust in systems, procedures, and each other under conditions where verification is limited. For some, this challenge is meaningful. It provides focus. It sharpens awareness. It reinforces discipline. For others, it is draining. Understanding this variability is difficult because the sample size is small and experiences are unique, but the pattern is clear enough to influence practice. As exploration pushes against deeper limits, psychological considerations become more prominent. Designers consider not just hull thickness and power capacity, but lighting, seating, noise levels, and interface design. Small improvements can reduce cognitive load and stress. Even so, these improvements do not change the fundamental nature of the environment. The deep ocean remains indifferent. It does not respond to comfort measures. It does not provide feedback that reassures. It does not soften its isolation. This indifference is perhaps the most psychologically challenging aspect of all. Humans are social creatures. We interpret environments through interaction. A landscape responds visually. Weather responds audibly. Other people respond emotionally. The deep ocean responds not at all. In that absence, the mind works harder to maintain equilibrium. This is not a flaw. It is a feature of human cognition. But it is a feature that has limits. As technology continues to advance, the psychological cost of extreme depth remains a constant factor. It cannot be engineered away entirely. It can be mitigated but not eliminated. This reality reinforces the trend toward indirect exploration. Sensors, autonomous vehicles, and remote observation allow data to be gathered without exposing humans to sustained psychological stress. Humans remain involved, but at a distance. This distance preserves well-being, but it also changes the nature of exploration. It becomes more analytical, less experiential. The visceral connection to place is mediated through screens and data. Whether this is a loss or a necessary adaptation is a matter of perspective. What is clear is that the deep ocean demands more than technical capability. It demands psychological resilience that few environments require, and even if individuals can endure the mental strain, the question remains whether enduring it repeatedly, over longer durations, is desirable or necessary. As this question is considered, attention shifts from individual experience to collective memory. What have past descents taught us? What lessons were learned not just about depth, but about the limits of persistence? And how those lessons continue to shape the way humans approach the deepest parts of their own planet. Every descent into the deepest parts of the ocean leaves behind more than data. It leaves behind lessons, often learned quietly, sometimes learned the hard way, and rarely forgotten by those who planned or experienced the journey. Because opportunities to descend into extreme depth are rare, each one carries disproportionate weight. There are no routine missions, no casual repetitions. Every attempt is treated as an event, studied long after it ends. One of the earliest lessons learned was that depth magnifies consequences rather than introducing new ones. Many of the failures that occur in the deep ocean are not exotic or mysterious. They are familiar engineering problems that behave differently under extreme conditions. A valve that sticks, a seal that degrades, a sensor that drifts out of calibration. On the surface, these are manageable issues. At depth, they become mission-ending. Early expeditions revealed that reliability matters more than innovation. Initial designs often attempted to push boundaries aggressively. New materials, novel configurations, unproven systems. The logic was understandable. If depth demanded new solutions, then bold design choices seemed appropriate. What repeated descents showed instead was that novelty introduced uncertainty, and uncertainty was costly. Over time, designs became more conservative. Proven components were reused, margins were increased. Simplicity was favoured over complexity. This shift did not slow progress. It stabilised it. Another lesson was that human presence adds both value and risk. The earliest crewed descents provided insights that machines could not at the time. Human observers could notice subtle details. They could adjust plans in real time. They could describe the experience in ways that enriched understanding. But these benefits came at a cost. Crewed missions required larger vessels, more life support, and greater safety margins. They increased the consequences of failure dramatically. Each crewed descent carried ethical and logistical weight that unmanned missions did not. As robotic technology improved, the balance shifted. Machines could collect data more consistently. They could operate longer. They could be lost without loss of life. Lessons from early crewed missions helped define where human presence was irreplaceable and where it was not. Most of the time, it was not. Past descents also revealed the importance of ascent planning. Many early missions focused heavily on descent capability. Reaching the bottom was the headline achievement. What followed often received less attention. Over time, it became clear that ascent was not merely a reversal of descent. It was a separate phase with its own risks and failure modes. Ballast systems became more robust. Redundant release mechanisms were added. automatic ascent triggers were implemented to activate if power was lost. These changes were responses to real failures, not theoretical ones. Several vehicles that reached extreme depth successfully failed to return because ascent systems did not function as intended. These losses underscored the need to treat ascent as the primary success criterion, not depth reached. Another lesson involved time at depth. Early missions sometimes attempted to maximize bottom time, reasoning that the rarity of descents justified extended stays. What experience showed was that longer duration increased risk disproportionately. Power consumption rose, system fatigue accumulated, psychological strain intensified. Later missions prioritized efficiency. Objectives were defined narrowly. Tasks were sequenced carefully. Time at maximum depth was minimized. This approach improved success rates and reduced unexpected complications. Communication strategies evolved as well. Initial assumptions often overestimated the reliability of acoustic communication. Early missions expected more consistent contact than was realistically possible. When signals failed or degraded, crews and operators were forced to improvise. Over time, communication protocols became more resilient. Missions were designed to function with minimal contact. Pre-planned decision trees replaced real-time guidance. Vehicles were programmed to behave conservatively if communication was lost. This autonomy reduced reliance on constant oversight, but it also required careful anticipation of scenarios that might occur. Navigation lessons were particularly influential. Early maps of the deep sea floor were coarse. Vehicles encountered slopes, ridges, and sediment conditions that were not predicted. Some became stuck, others landed unevenly. These experiences emphasized the need for better mapping and cautious movement. As mapping technology improved, missions incorporated higher resolution bathymetric data. Even then, operators learned not to trust maps completely. The seafloor at extreme depth can change. Sediment shifts. Small collapses occur. Caution became standard practice. Another significant lesson concerned redundancy. It became clear that redundancy is not always beneficial if it increases complexity beyond manageable levels. Adding backup systems adds weight, power consumption, and failure points. Each additional component introduces interfaces that can fail. Designers learned to prioritize redundancy where it mattered most and simplify elsewhere. Hull integrity, life support, and ascent systems received the most attention. Secondary functions were sometimes sacrificed. This prioritization reflected a deeper understanding of risk. Not all failures are equal. Some can be tolerated, others cannot. The behavior of materials under repeated pressure cycles was another area of learning. Early missions sometimes reused components without fully accounting for cumulative stress. Over time, fatigue effects became apparent. Materials that performed well on first descent showed degradation after multiple cycles. This led to stricter inspection protocols and limited reuse of critical components. Some parts were retired after a single mission. Others were subjected to extensive testing between dives. The lesson was simple. Pressure leaves a mark, even when nothing appears broken. Human factors lessons emerged as well. Crewed missions highlighted the importance of clear communication within the vessel. Procedures needed to be explicit. Roles needed to be defined. Ambiguity increased stress and slowed response. Training emphasized not just technical skill, but psychological preparedness. Crews learned to recognize signs of cognitive overload and manage it proactively. Checklists became more detailed. Decision-making frameworks were formalized. These lessons carried over into surface operations too. Teams learned to manage uncertainty, accept incomplete information, and resist the urge to overinterpret sparse data. Perhaps the most important lesson from past descents was about expectations. Early exploration often framed the deepest ocean as a frontier to be conquered. Depth records were celebrated. Milestones were emphasized. Over time, this framing softened. Explorers and engineers came to see extreme depth less as a challenge to overcome and more as an environment to engage with cautiously. Success was redefined, not by how deep one went, but by what was learned and whether the vehicle returned intact. This shift changed how missions were communicated to the public and funded by institutions. The emphasis moved from spectacle to science. There were also lessons about limits. Some goals once considered achievable were quietly abandoned. Permanent installations, long-term human habitation, frequent crewed descents. These ideas faded not because of failure, but because accumulated experience showed they were impractical. This acceptance was not defeat, it was refinement. Knowing where limits lie allows resources to be allocated more effectively. It prevents repeated mistakes. It focuses effort where progress is possible. Lessons from past descents also influenced policy. Regulatory frameworks evolved to reflect the risks involved. Authorization processes became more stringent. Safety reviews more thorough. International cooperation increased as expertise was scarce and costly. Sharing lessons became essential. No single organization could afford to learn everything independently. Perhaps the quietest lesson of all was about humility. The deep ocean does not reward bravado. It rewards patience, precision, and restraint. Those who approach it with respect tend to succeed more often than those who attempt to dominate it. This humility extended beyond engineering. It shaped scientific questions. Researchers became more selective about what they sought to study. They prioritized questions that justified the risk and expense. Over time, a culture emerged around deep-sea exploration. A culture defined by caution rather than conquest. This culture continues to influence decisions today. It explains why progress appears slow from the outside, why missions are rare, why announcements are measured. The lessons learned from past descents are not dramatic stories of triumph or disaster. They are accumulated understandings, adjustments made quietly, expectations recalibrated. They form a kind of institutional memory that guides each new attempt. As technology advances, these lessons remain relevant. New materials and systems do not erase the environment. They must operate within it. The deepest parts of the ocean have not changed. Pressure remains constant, darkness persists, isolation endures. What has changed is how humans respond. Each descent has narrowed the gap between ambition and reality. It has clarified what is worth attempting and what is not. It has shaped a philosophy of exploration that values knowledge over presence. And yet, even with all these lessons absorbed, curiosity does not disappear. The question shifts from how to go deeper at any cost to whether deeper presence is necessary at all. This question opens the door to another realization. Perhaps the reason humans have not established a lasting foothold in the deepest ocean is not just because it is difficult, but because the lessons learned suggest that doing so may not be the best use of our effort. That realization leads naturally to the next consideration. If we understand the environment better now, why have we still not built anything permanent there? What exactly stops us from staying, even briefly, on a repeating basis? The answer lies not in what we have learned, but in what those lessons imply. The idea of a permanent human presence carries a certain weight. It suggests stability, continuity, and control. When humans establish a lasting foothold somewhere, it usually marks a transition from exploration to occupation. Camps become stations. Visits become routines. Risk becomes managed rather than confronted each time anew. In the deepest parts of the ocean, that transition has never happened. This absence is not an oversight. It is the result of accumulated understanding, shaped by physics, biology, psychology, and economics, all pointing in the same direction. Building a permanent presence in the Mariana Trench is not merely difficult. It is misaligned with how that environment behaves and how humans must operate to survive. The first barrier is structural persistence. Any permanent structure at extreme depth would be subjected to constant, unrelenting pressure. Unlike a submersible, which is designed to endure pressure for a limited duration, a stationary habitat would need to endure it indefinitely, not for hours or days, but for years. Pressure does not fatigue quickly, but materials do. Even the strongest alloys experience creep, the slow deformation of materials under sustained stress. At the surface, creep occurs over long time scales and is often negligible. Under thousands of atmospheres, creep accelerates. Microscopic changes accumulate. Shapes shift imperceptibly until tolerances are exceeded. A permanent structure would need constant inspection and maintenance to detect and address these changes. But inspection itself requires human or robotic presence. Maintenance requires tools, replacement parts, and repeated interaction with the structure. Every maintenance visit would reintroduce the same risks as a descent mission. Pressure cycles, ascent hazards, communication limits, psychological strain. A permanent structure would not eliminate risk, it would multiply exposure to it. Then there is the issue of sealing. A habitat must remain sealed against the surrounding environment, not temporarily, but continuously. Seals age, polymers degrade, interfaces between different materials expand and contract differently over time. Even in benign environments, maintaining airtight seals indefinitely is challenging. At extreme depth, the environment actively works against sealing. Pressure compresses materials, salt water infiltrates microscopic gaps, corrosion accelerates. Microbial activity, even in cold environments, can affect surfaces over time. A single compromised seal could flood a habitat rapidly. There would be no gradual warning, no manageable leak. The environment would reclaim the space instantly. This risk cannot be eliminated by redundancy alone. Multiple seals increase complexity. Complexity increases failure points. At some level, the probability of failure over time approaches certainty. Permanent presence assumes maintainability. The deep ocean resists maintenance. Power is another fundamental limitation. A habitat requires energy for lighting, life support, communication, heating, and operation of systems. At the surface, energy can be generated easily. In space, solar power is abundant. In the deep ocean, sunlight does not exist. Power would need to be supplied through cables from the surface, generated chemically, or produced via nuclear sources. Each option carries serious drawbacks. Cables must descend kilometers through water, withstand pressure, avoid damage from currents, and remain intact indefinitely. A damaged cable would cut power instantly. Repairing it would require a mission nearly as complex as building the habitat in the first place. Chemical power sources are finite. They require resupply. Resupply requires ascent and descent cycles, reintroducing risk repeatedly. Nuclear power introduces regulatory, safety, and ethical concerns. It also introduces heat management challenges in an environment where thermal dissipation behaves differently. While theoretically possible, nuclear solutions add layers of complexity that amplify consequences of failure. Life support systems face similar constraints. Humans require oxygen, water, food, waste management, and temperature regulation. These systems can be closed-loop to an extent, but not perfectly. Over time, losses occur. Filters clog, chemical balances drift, components wear out. On the International Space Station, life support systems are maintained constantly by crews and supported by regular resupply missions. That model works because access is feasible and rescue is possible. At extreme depth, resupply is hazardous. Evacuation is nearly impossible. A life support failure would not allow time for response. Even if technical challenges were somehow solved, human factors remain. Living at extreme depth would mean prolonged confinement in a small, sealed environment with no natural light, limited communication, and no escape. The psychological cost described earlier would not diminish with familiarity. It would accumulate. Long-term studies of isolated environments show that even highly trained individuals experience mood changes, cognitive fatigue, and interpersonal strain over time. These effects can be mitigated but not eliminated. A permanent presence would require rotating crews to prevent burnout. Rotation requires regular ascent and descent. Each rotation carries risk. Over time, cumulative risk becomes unacceptable. This is a key difference between permanence and visitation. A temporary mission concentrates risk into a single, carefully managed event. A permanent presence distributes risk across countless events. Statistically, this increases the likelihood of serious incidents. There is also the question of purpose. Why build a permanent presence at extreme depth? Scientific research does not require continuous human presence. Data can be collected by instruments. Samples can be retrieved by robotic vehicles. Observations can be automated. Human presence is valuable for flexibility and interpretation, but those advantages diminish as environments become more hostile. At some point, the cost outweighs the benefit. Economic incentives are also limited. Unlike shallow waters, the deepest ocean offers few resources that cannot be accessed more safely elsewhere. Deep-sea mining targets areas much shallower than the Mariana Trench. Fisheries do not operate at extreme depth. There is no strategic shipping advantage. Without clear economic return, funding a permanent habitat becomes difficult to justify. Governments and institutions weigh cost against benefit. Extreme depth offers knowledge, but not continuous utility. This does not mean the knowledge is unimportant. It means it does not require habitation. Another constraint is legal and ethical. International waters are governed by complex treaties. Establishing permanent structures raises questions about jurisdiction, responsibility, environmental impact, and liability. Who maintains the structure? Who is responsible if something goes wrong? Who decides who can access it? These questions are manageable in environments where access and enforcement are feasible. At extreme depth, enforcement is theoretical. Environmental considerations also play a role. Deep-sea ecosystems are fragile in their own way. Disturbance persists longer, recovery is slow. A permanent structure would alter local conditions permanently. It would introduce noise, heat, light, and chemical changes. The long-term impact of such disturbance is poorly understood. Without clear necessity, imposing it becomes ethically questionable. The absence of a permanent presence is therefore not a failure of imagination. It is an outcome of restraint. Human history is full of examples where restraint arrived late, after damage was done. In the deepest ocean, restraint arrived early, guided by experience rather than regret. This restraint is reinforced by the nature of deep-sea exploration itself. Unlike space, which offers multiple destinations and gradients of difficulty, extreme depth is singular. There is one deepest point. Reaching it is an event. Staying there does not unlock new territory. It does not open pathways to further expansion. Once the bottom is reached, there is nowhere else to go. This makes permanence less appealing. A permanent presence usually serves as a base for further exploration. At the Challenger Deep, there is no beyond. Technology development also follows incentives. Engineers innovate rapidly when there is demand for repeated use. Aviation improved because people flew often. Space technology advanced because multiple missions built on each other. Deep-sea extreme-depth missions are rare by necessity. There is no feedback loop of frequent use. Without frequent use, technologies do not mature into everyday reliability. They remain specialized, expensive, and fragile. Building permanent infrastructure on such foundations is risky. There is also a cultural factor. Human societies invest in places that can support stories, continuity, and identity. Research stations in Antarctica, despite their isolation, still exist within an environment where rescue is possible, seasons change, and the sky provides orientation. The deep ocean offers none of this. It is difficult to imagine a sense of place forming in total darkness, under crushing pressure, with no visible connection to the world above. This matters because permanence is not just technical, it is social. People need reasons to be somewhere, not just tasks, but meaning. In environments where survival dominates attention, meaning narrows. For short missions, that narrowing is acceptable. For long-term presence, it becomes unsustainable. Another reason permanence has not emerged is that success criteria are different. In many domains, permanence signals success. In extreme depth, success is defined by safe return. A mission that returns intact is a success regardless of how long it stayed. This metric discourages prolonged exposure. It values caution. It rewards designs that minimize time at risk. Over decades, this perspective has shaped institutional memory. Decision makers internalize the lesson that deeper does not mean longer. This is why proposals for permanent deep ocean habitats rarely progress beyond conceptual stages. They are fascinating thought experiments. They inspire imagination. But when evaluated rigorously, they falter. Not because they are impossible in principle, but because they are impractical in context. The Mariana Trench does not invite settlement. It does not offer resources that require it. It does not support incremental expansion. It does not allow maintenance to become routine. It remains a place of visits, not stays. This does not mean the future holds no surprises. Technology evolves. Materials improve. Autonomy increases. It is possible that new approaches will change how humans interact with depth. But even then, the fundamental constraints remain. Pressure will not diminish. Darkness will not lift. Distance will not shrink. Any permanent presence would need to accept these constraints fully, not temporarily. For now, the lessons learned point consistently in one direction. Use machines, minimize exposure, observe, measure, and leave. This approach has yielded remarkable knowledge without demanding permanence. The absence of a permanent presence is therefore not a gap waiting to be filled. It is a conclusion reached gradually, reinforced by experience. As attention shifts away from habitation and toward intention, a subtler realization emerges. Perhaps the reason humans have not stayed is not just because the environment is hostile, but because the ocean itself does not require us to be there to be understood. And perhaps in that understanding there is a different kind of respect, one that acknowledges boundaries without needing to cross them. As exploration continues, this respect shapes the questions we ask next. Not how to stay, but why we feel the need to, and what it means to leave some places as places we visit only briefly, if at all. The ocean's claim on the unknown is not loud. It does not announce ownership. It does not mark territory or defend boundaries. It simply remains, vast and unchanged, allowing curiosity to approach, but never fully surrendering what lies within it. This claim is not enforced through resistance alone. It is enforced through scale, patience, and indifference. The ocean does not chase explorers away. It outlasts them. For centuries, humans have approached the sea as something to be crossed, mapped, harvested, and eventually understood. Coastlines were charted, trade routes established, depths measured. Each advancement created the sense that the unknown was shrinking. That knowledge, given enough time, would fill in every blank. The deepest ocean quietly challenges that assumption. Despite advanced sonar, satellite mapping, autonomous vehicles, and decades of research, large portions of the seafloor remain poorly characterized. Not because they are inaccessible in principle, but because access is costly, slow, and fleeting. Each visit reveals something, but never enough to feel complete. The Mariana Trench exemplifies this dynamic. It is known in outline, but not in detail. Its depth is measured, but its contours shift. Its biological communities are sampled, but not fully catalogued. Its geological processes are inferred, but not observed continuously. The unknown persists not as a gap in effort, but as a consequence of environment. The ocean's silent claim is reinforced by how information is gathered. Data from extreme depth arrives fragmented. Short video clips, sensor readings, isolated samples. Each piece is valuable, but none provide continuity. There is no long-term, uninterrupted observation. This lack of continuity matters. Understanding complex systems requires time. Patterns emerge through repetition. Variations reveal structure. In the deep ocean, repetition is rare. Each mission is separated by years. Conditions change subtly between visits. The environment resets. The ocean does not allow us to watch it the way we watch the sky or the land. This limits certainty. Scientists build models, but models rely on assumptions. Assumptions must be tested. Testing requires presence. Presence is constrained. As a result, much of what we know about the deepest ocean is provisional. It is the best explanation given limited data, not a final account. This provisional knowledge is uncomfortable for a species accustomed to closure. Humans prefer complete maps, definitive answers, and boundaries that feel settled. The deep ocean resists this preference. It also resists narrative. Stories about exploration often follow a familiar arc. There is a journey, there is a challenge, there is a breakthrough, there is resolution. The ocean's depths do not fit neatly into this structure. There is no final descent that reveals everything, no moment where the unknown becomes known and stays that way. Each descent adds detail but also raises new questions. This open-endedness reinforces the ocean's claim. It suggests that some unknowns are not waiting to be solved once, but to be revisited indefinitely. That understanding is not a destination, but a relationship. The ocean's claim is also temporal. Human projects operate on timelines measured in years or decades. The trench exists on geological timescales. Its formation, evolution, and eventual disappearance span millions of years. From that perspective, human exploration is episodic. We arrive briefly, we observe, we leave, the ocean continues. This mismatch in timescale affects how much influence humans can exert. Long-term change requires sustained presence. The deep ocean does not allow sustained presence easily. Even when human activity does leave traces, those traces fade. Sediment covers objects. Chemical signatures disperse. Physical disturbances smooth out. Over time, evidence of intrusion diminishes. This erasure reinforces the sense that the ocean retains ownership. Human influence does not accumulate the way it does on land. The unknown persists because the environment does not preserve our interventions. There is also a cognitive aspect to this claim. Humans understand the world through patterns that align with our senses and experiences. The deep ocean violates many of these patterns. Pressure, darkness, and isolation distort perception. Familiar cues are absent. The environment feels abstract. Abstraction makes understanding harder. When environments cannot be experienced directly and continuously, they remain conceptually distant. We can describe them mathematically. We can simulate them, but they do not integrate into everyday intuition. This distance maintains the unknown. The ocean's silence contributes as well. Unlike environments that respond audibly or visibly to disturbance, the deep ocean absorbs sound and light. Actions do not produce clear feedback. The environment does not announce change. This lack of feedback limits learning. Humans learn best when actions produce observable consequences. In the abyss, consequences are delayed, subtle, or invisible. This reinforces caution. It slows progress. It preserves mystery. There is also the matter of selectivity. Not everything unknown is equally pursued. Humans prioritize unknowns that promise utility, survival, or expansion. The deepest ocean offers knowledge but not immediate application. This does not diminish its importance. It explains why exploration remains intermittent. Resources are finite. Attention is directed where returns are clearer. The ocean's claim on the unknown is therefore partly a consequence of human choice. We choose not to pursue complete understanding at any cost. We accept partial knowledge. This acceptance is not always explicit, but it is evident in practice. The deep ocean also challenges the idea that unknowns exist to be claimed at all. Much of human exploration has been driven by ownership. Mapping territories, naming features, establishing presence. In the deepest ocean, ownership feels abstract. There is nothing to possess, nothing to control. Naming a trench does not grant access. Measuring depth does not grant mastery. The ocean remains unchanged by recognition. This undermines a familiar motivation. Exploration without ownership feels incomplete to some, but it may be more appropriate here. The unknown remains not because humans are incapable, but because the environment does not reward completion. Each descent ends the same way, with ascent, with return, with the unknown closing behind. This pattern reinforces humility. It reminds explorers that knowledge can be gathered without dominance. That understanding does not require permanence. The ocean's claim is also ecological. Deep-sea ecosystems operate under conditions that are poorly understood and easily disrupted. The more we learn, the clearer it becomes that disturbance carries long-lasting consequences. This knowledge introduces restraint. Curiosity is balanced against preservation. Exploration is weighed against impact. In this balance, the unknown is sometimes left intact deliberately. The ocean does not demand this restraint. Humans impose it themselves. But the environment's fragility makes the decision feel necessary. This self-imposed boundary reinforces the ocean's claim. We choose not to know everything if knowing requires harm. There is also a philosophical dimension. Some unknowns persist because they challenge our frameworks. They do not fit neatly into existing categories. The deep ocean hosts forms of life and geological processes that do not align with surface-based intuition. These differences require new ways of thinking, new models, new metaphors. Progress is slow because conceptual change lags behind observation. The unknown persists not because it is inaccessible, but because it is unfamiliar in a fundamental way. The ocean does not conform to our expectations. This resistance to expectation keeps the unknown alive. Even with advanced technology, the ocean controls the terms of engagement. It determines duration, frequency, and depth of interaction. Humans respond within those limits. This asymmetry defines the relationship. The ocean does not compete. It does not race. It waits. And waiting is something humans do not do easily. Over time, this dynamic shapes how the deepest ocean is perceived, not as a frontier to be conquered, but as a boundary to be acknowledged, not as an absence to be filled, but as a presence that persists. The unknown becomes less of a problem to solve and more of a condition to accept. This acceptance does not halt exploration. It changes its tone. It becomes quieter, more deliberate, less urgent. The ocean's silent claim is not a refusal. It is a reminder that not all unknowns are temporary, that some exist because the environment sustains them. That knowledge can grow without erasing mystery. As exploration continues, this reminder becomes more prominent. Each new mission adds detail without dissolving the whole. Each answer generates further questions. The unknown remains not because humans stop asking, but because the ocean continues to answer selectively. This selectivity is not intentional. It is structural. The deep ocean offers glimpses, not panoramas, moments, not continuity, data points, not narratives. In this way, the ocean retains its claim. It does not guard the unknown aggressively. It simply does not give it all away. And perhaps that is why the deepest parts of the ocean remain compelling, not because they are unreachable, but because they remain unresolved. They remind us that exploration does not always end with clarity. Sometimes it ends with respect. And in that respect, a different question begins to form. If the ocean keeps its unknowns not through force, but through endurance, What does that say about the future of our attempts to go deeper? What happens when curiosity meets acceptance, and whether the deepest barrier is one of technology or of intention? The question of whether humans will ever go deeper than this tends to arrive quietly, almost as an afterthought. It follows naturally from everything learned so far, from pressure and darkness to communication and psychology. It is not a question driven by impatience, it is driven by reflection. Depth, after all, is a measurable thing. Numbers invite comparison. Records suggest progress. Once a deepest point is identified, it feels incomplete to stop there. The idea of deeper carries with it the promise of extension, of continuation, of something beyond the last known limit. But the ocean does not organise itself around human expectations. To ask whether we'll go deeper than the deepest known point is to assume that depth behaves like distance, that there is a logical next step, that technology, given enough time, will extend reach incrementally until the boundary dissolves. In many environments, that assumption holds. On land, mountains were climbed one by one. In the air, altitude increased gradually. In space, orbits extended outward. Each advance built on the last, opening new ranges. The deep ocean does not offer that gradient. The Mariana Trench already represents the lowest accessible point of Earth's surface. There is no deeper basin waiting to be reached in the same way. There is no series of progressively deeper steps that lead somewhere else. The trench is not a gateway, it is a terminus. This changes the nature of the question. Going deeper does not unlock new regions, it does not reveal a broader expanse beyond. It pushes further into the same environment, with increasing cost and diminishing returns. That does not mean it is impossible. It means it must be justified differently. From a purely technical perspective, going deeper than current human descents is conceivable. Materials can be strengthened, hulls can be thickened, systems can be simplified, autonomous vehicles can be designed to tolerate greater pressure. Incremental gains are possible, but each incremental gain comes at exponential cost. Pressure increases linearly with depth, but engineering difficulty does not. It accelerates. Each additional meter adds stress to every component. Safety margins shrink. Testing becomes harder. Failure becomes more catastrophic. This creates a curve where effort rises sharply, while benefit rises slowly. At some point, the curve flattens. Progress becomes technically impressive but practically marginal. This is where intention becomes more important than capability. Why go deeper? Not because it is there, but because what is gained justifies the cost. For human presence, the justification becomes increasingly difficult. Crude descents already operate at the edge of practicality. Extending them deeper would amplify every risk described earlier. Pressure, isolation, communication limits, rescue impossibility, psychological strain. None of these diminish with experience, they intensify. Human presence does not scale well with depth. Machines scale better, but not infinitely. Autonomous vehicles can be designed without life support, without windows, without concern for psychology. This makes them more tolerant of depth. But they still face material limits, power constraints, and communication challenges. They also face diminishing informational returns. At extreme depth, environmental conditions stabilize. Temperature, pressure, and darkness reach steady states. Geological and biological variation continues, but at smaller scales. Each additional meter explored yields less novelty than the last. This does not make the information unimportant. It makes it incremental. Funding agencies, institutions, and research organizations must decide whether incremental knowledge at extreme cost is preferable to broader understanding elsewhere. Often, the answer is no. This does not mean exploration stops. It shifts focus. Rather than going deeper vertically, exploration spreads horizontally, mapping larger areas at known depths, observing changes over time, understanding interactions between systems. studying how deep environments connect to surface processes. These questions require presence, but not maximal depth. In this sense, the deepest point becomes less of a goal and more of a reference. It marks an endpoint that helps define the range, not a target that demands repetition. There is also a cultural shift influencing this question. Earlier eras of exploration were driven by records. Firsts, deepest, highest, farthest. These achievements captured attention and justified risk. Modern exploration increasingly values understanding over spectacle. Success is measured by insight, not extremity. This shift reduces pressure to go deeper simply to prove that it can be done. It also aligns with ethical considerations. Sending humans into environments where rescue is impossible demands extraordinary justification. Repeating such missions solely to extend a record becomes harder to defend. Public perception matters here. Societies are less willing to accept loss of life for symbolic achievement. The threshold for acceptable risk has changed. This influences decisions about depth. There is also the question of what deeper even means. The Mariana Trench is the deepest known point relative to sea level, but depth can be defined differently. Beneath the seafloor lies another world, layers of sediment, crust, mantle. Humans do not access these physically, but study them indirectly through seismic waves and drilling. In that sense, exploration already extends deeper, just not through direct presence. This indirect exploration often yields more information than physical descent. Seismology reveals structure, geochemistry reveals composition, models reveal dynamics. These methods bypass the need for extreme depth exposure while expanding understanding. This raises a subtle point. Perhaps the future of deep exploration is not deeper presence, but deeper inference, using surface-accessible tools to probe inaccessible environments. Accepting that some places are better understood indirectly, this approach has precedent. Humans understand the core of the Earth without visiting it. We understand distant stars without reaching them. Depth, like distance, does not always require proximity. The desire to go deeper is therefore not universal. It competes with other priorities: climate change and biodiversity loss, ocean acidification, and pollution demand attention. Many of these processes affect deep environments indirectly. Understanding them requires resources. Allocating those resources to pushing a few hundred meters deeper into an already hostile environment may not be the most effective choice. This does not diminish the symbolic power of depth. It contextualizes it. The deepest ocean becomes a reminder of limits rather than an invitation to exceed them. There is also a technical reality that often goes unnoticed. Testing at extreme depth is inherently limited. Pressure chambers can simulate pressure, but not the full combination of conditions present in the trench. Cold, corrosion, time, and isolation interact in complex ways. Each deeper mission increases uncertainty rather than reducing it. This uncertainty makes engineering validation difficult. Systems cannot be proven safe through repeated testing. Each test is unique. This contrasts with aerospace, where components undergo thousands of test cycles. Reliability improves through repetition. Deep-sea extreme depth exploration does not allow this. Without repetition, confidence remains fragile. This fragility discourages pushing further. Another factor shaping the future is autonomy. As artificial intelligence and robotics advance, machines will handle more complex tasks with less oversight. This may extend operational depth gradually. But even advanced autonomy does not eliminate fundamental constraints. Power remains finite, materials remain vulnerable, communication remains limited. Autonomy changes who is exposed, not what the environment demands. It also raises new questions. How much autonomy is acceptable when failure means loss of expensive equipment and irreplaceable data? How much decision-making should be delegated to machines operating beyond human supervision? These questions are unresolved, As a result, progress remains cautious. It is also worth noting that deeper is not always better. Many unanswered questions about the deep ocean exist at shallower depths. Biodiversity gradients, carbon cycling, geological processes, human impacts. These areas offer rich scientific returns without extreme risk. Focusing solely on maximum depth can obscure these opportunities. The deepest point draws attention, but it is not representative of the deep ocean as a whole. Understanding comes from breadth as well as depth. There is a philosophical element to this as well. Human curiosity often pushes toward boundaries. Once a boundary is reached, the impulse is to cross it. But some boundaries function differently. They define the edge of a domain rather than a gateway to another. The deepest ocean appears to be such a boundary. Crossing it does not reveal a new domain. It intensifies the same conditions. This challenges the assumption that exploration must always proceed outward or downward. Perhaps the more meaningful question is not whether we will go deeper, but whether depth itself remains the right axis of exploration. As technology evolves, other axes emerge. Time, resolution, interaction, integration. Long-term observation at moderate depth may reveal more than brief contact at extreme depth. High-resolution mapping may reveal patterns missed by single-point visits. Integration of data across disciplines may provide insights no single descent could offer. These approaches do not reject depth, they reposition it. The deepest point remains significant, but not dominant. There is also the question of restraint. Choosing not to go deeper can be an active decision rather than a limitation. It can reflect prioritization rather than incapacity. In a world with finite resources and many urgent challenges, not every boundary must be pushed. The deep ocean will remain. It does not require immediate conquest. It does not demand urgency. This patience stands in contrast to human timelines. The ocean can wait. This asymmetry suggests that the question of going deeper may not have a definitive answer. It may depend less on technology and more on values. What do we want from exploration? Is it demonstration of capability? Is it accumulation of knowledge? Is it stewardship? Is it curiosity for its own sake? Different answers lead to different priorities. If the goal is knowledge, then going deeper is one tool among many, not an end in itself. If the goal is presence, then deeper presence becomes less justifiable as cost rises. If the goal is understanding Earth as a system, then extreme depth is one piece of a larger puzzle. In that context, the deepest point is important, but not singular. This reframing does not diminish the achievements of those who reached it. It places them within a broader narrative. They did not open a path to routine access. They defined a limit. Defining limits is as important as crossing boundaries. It clarifies where effort yields returns and where it does not. The Mariana Trench serves as such a clarification. It shows that human exploration does not always expand smoothly. Sometimes it encounters a wall that is not meant to be scaled repeatedly. That wall is not insurmountable. It is simply not useful to climb again and again. As technology advances, it is possible that new methods will alter this assessment. Materials unknown today may behave differently. Power sources may improve. Autonomy may reduce cost. But even if these developments occur, the fundamental question remains: what would be gained by going deeper than this? Until that question has a compelling answer, the deepest ocean will likely remain a place of rare visits rather than sustained progress. Curiosity will persist. Occasional missions will occur. Data will accumulate slowly. But the trench will not become a corridor. It will remain a reference point, a place that marks where human presence fades and indirect understanding begins. In that sense, the future of depth is not a straight line downward. It is a circle around understanding. The deepest ocean does not demand that we go deeper. It asks whether we know enough to decide not to. And that decision, like the trench itself, sits quietly beneath the surface, waiting to be acknowledged. The Mariana Trench does not reject us loudly. It does not rise up, block our path, or make demands. It does something far more effective. It remains exactly as it is. After everything we have learned, after every descent, every calculation, every reinforced hull and carefully planned mission, the trench still sits beneath the Pacific with the same conditions it has always had. The pressure has not softened. The darkness has not lifted. The distance has not shortened. Nothing about the environment has adjusted itself to human persistence. And in that quiet consistency, the trench continues to say no. Not no to curiosity, not no to knowledge, but no to permanence, no to comfort, and no to the idea that every place on Earth is meant to be occupied simply because we can reach it. This is not a failure of ambition. It is an encounter with a boundary that does not behave like others we have crossed. For most of human history, boundaries were temporary. Mountains could be climbed, oceans could be crossed, deserts could be traversed. Each challenge eventually gave way to familiarity. Routes became roads. Camps became cities. The unknown became mapped, named, and settled. The Mariana Trench has not followed that pattern. We have reached it. We have measured it. We have looked around briefly and returned. And then we have done something unusual. We have mostly stopped. Not because we ran out of ideas, but because the ideas began to converge on the same conclusion, that the cost of staying outweighs the value of doing so, that presence does not equal understanding, that control is not always the appropriate response to discovery. The trench still says no because it does not need to say yes. It offers no incentive to linger, no resources that demand extraction, no strategic advantage that requires occupation. No environment that can be shaped gradually into something more accommodating. It offers knowledge, but only in fragments, and only on its terms. This has quietly reshaped how humans relate to it. Instead of building bases, we build instruments. Instead of sending people repeatedly, we send machines selectively. Instead of planning permanence, we plan brief contact followed by careful analysis elsewhere. This is a different mode of exploration. Less dramatic, less visible, but not lesser. It reflects a growing recognition that not every environment responds well to human presence, and that insisting on presence can sometimes reduce understanding rather than enhance it. The trench still says no in another way as well. It says no to narrative closure. There is no final descent that resolves everything, no last expedition after which the place becomes familiar. Every visit adds information, but also reinforces how much remains unknown. The seafloor shifts, life surprises, measurements adjust, models refine. The story does not end. It loops. For a species that prefers conclusions, this looping can feel unsatisfying. But it may be more honest. The deep ocean does not exist to be completed. It exists to be engaged with cautiously, intermittently, and with acceptance of limits. This acceptance does not diminish curiosity. It refines it. Curiosity becomes less about conquest and more about listening, less about reaching further and more about understanding better, less about proving capability and more about recognizing context. In this sense, the trench has already changed us. Not by yielding, but by remaining firm. It has taught engineers to value simplicity over bravado. It has taught scientists to design questions that can be answered without continuous presence. It has taught institutions to weigh human risk differently. It has taught explorers to plan for return rather than endurance, and it has taught a quieter lesson as well, that some places do not need us. This is not a comfortable idea. Human history is built on interaction, modification, and settlement. We shape environments and in turn are shaped by them. The idea that an environment can remain largely untouched by choice, rather than inability, challenges deeply held assumptions. Yet that is exactly what has happened here. The trench remains largely as it was before the first descent. Its ecosystems continue on timescales indifferent to human schedules. Its geology continues its slow motion beneath tectonic plates. Its darkness remains uninterrupted. Our presence when it occurs is brief. That brevity has become part of the relationship. The trench still says no because it does not negotiate. It does not compromise. It does not gradually soften as familiarity increases. It applies the same conditions every time, whether it is the first visit or the 10th. This consistency makes it reliable in a way. We know what it will do. We know how it will respond. It will not adapt to us. It will not adjust margins. It will not offer second chances. That reliability is what allows exploration at all, and it is also what prevents escalation into permanence. In a world where many boundaries are shifting, eroding, or being pushed outward relentlessly, the Mariana Trench stands as one that holds. Not because humans lack the tools to challenge it, but because challenging it repeatedly offers diminishing returns. There is also something quietly grounding about this. The trench reminds us that Earth is not fully domesticated, that beneath layers of infrastructure and familiarity, there are environments governed by rules older than human presence and indifferent to it. This reminder arrives without spectacle. It arrives through data that shows pressure curves climbing steadily, through mission logs that record careful descent and immediate ascent, through engineering reports that conclude not with triumph, but with recommendations for caution. It arrives through absence of cities, absence of stations, absence of routine, and in that absence meaning accumulates. The trench still says no, and that no has been heard, not as a challenge to be overcome, but as information to be integrated. We integrate it by shifting focus, by exploring broadly rather than deeply, by observing over time rather than occupying space, by accepting that some forms of understanding do not require constant presence. This integration is visible in how deep-sea science is conducted today. Long-term sensors at moderate depths, autonomous vehicles mapping wide areas, data synthesis across disciplines, fewer record attempts, more contextual studies. Depth remains part of the picture, but not the axis around which everything turns. The trench becomes a reference point rather than a destination. It marks where the ocean becomes something else entirely, where the rules governing human activity change so fundamentally that the usual responses no longer apply. This marking is valuable. It tells us where engineering transitions from practical to theoretical, where rescue transitions from delayed to absent, where presence transitions from possible to symbolic. Knowing where these transitions occur allows for better decisions elsewhere. It informs how we design submersibles for shallower depths, how we plan autonomous missions, how we assess risk, how we allocate resources. The trench's refusal is not sterile. It is informative. It is also humbling. Humility is not often associated with exploration. Exploration is framed as expansion, assertion, and achievement. Yet humility plays a crucial role in sustainable inquiry. Recognizing limits allows curiosity to persist without becoming destructive. It prevents obsession with extremes from overshadowing broader understanding. The trench has imposed humility not through catastrophe but through clarity. It has shown us what it takes to go there, what it costs to stay briefly, and what it would cost to remain. And in doing so, it has made the choice clear. We can visit, we can observe, we can learn, but we do not belong. This does not diminish the value of those who have gone. On the contrary, their journeys are significant precisely because they were rare, deliberate, and constrained. Each descent represents a careful negotiation with an environment that does not yield easily. Those journeys expand understanding while respecting limits. As technology advances, it is likely that humans will continue to return occasionally. New vehicles will descend, new data will be gathered, new questions will be asked, but the pattern will likely remain the same: brief contact, careful observation, return. the trench will still say no to permanence. And perhaps that is not something to overcome. Perhaps it is something to preserve. In a world where so many boundaries are pushed until they break, having one that holds quietly can be instructive. The Mariana Trench reminds us that exploration does not always end with settlement, and that understanding does not always require occupation. Some places teach best by remaining just out of reach. As you rest now, wherever you are, far above that depth, surrounded by air instead of water, light instead of darkness, and sounds that arrive without delay, it's worth noticing how stable those conditions feel. They are not universal. They are specific. They are the reason we can pause, reflect, and listen to questions like these without thinking about pressure gauges or hull integrity. Far below, the trench continues on in silence, not hostile, not welcoming, just present. And in that presence it continues to say no, not as a rejection, but as a reminder that not every boundary exists to be crossed. Some exist to tell us where we are.